Hello, everyone. Welcome back to Ask a Scientist Gaming. I'm Ken Hansen, Associate Professor in the Department of Chemistry and Biochemistry at Florida State University. I do all things light matter interaction, molecules driven by light, photons to do catalysis, solar cells, chemical transformations, whatever it might be. But more importantly, joining me today is Professor Sachin Shanbhag. Sachin, if you wouldn't mind introducing yourself.
Hi, I'm Sachin Shanbhag. I'm a professor in the Department of Scientific Computing at Florida State. And my research is mostly in computational material science. So I study materials, mostly polymers. And I study them in a sort of a different way. I do experiments, but I don't do experiments in a wet lab. I do experiments on computers. So basically, we write models for them. We write models for these polymeric materials, and we use big computers to solve these models.
So, what do you typically teach?
So I'm trained as a chemical engineer. So I've taught a lot of different classes over my career. So I've taught classic chemical engineering classes like thermodynamics and kinetics and controls. But now in the Department of Scientific Computing, most classes I teach are related to algorithms, right? So some form of algorithms, essentially how to solve equations on a computer.
Makes sense. Equally important, what are we starting with tonight? What game?
We're going to start with Dynamite Dan,
Dynamite Dan, ladies and gentlemen.
which is a
All right, so before you start, we have Redeem Take a Drink by a guy doing guy things. So cheers, Sachin. Thank you for joining me. Everyone, thank you for joining us on a Wednesday night. Hopefully you have drinks in front of you. By the way, tonight we're drinking High Life from Cigar City. This is a Tampa brewed beer. Any particular reason for this choice?
No, I just like it. I think that's good enough.
It's a good drink. I'll put a link in there for you guys if you want to see. There's Cigar City's website. So, Sachin, you ready?
Yes.
Start doing it.
So I have to warn you that I suck at this.
How long has it been? You played this a bunch when you were younger.
Yes, it's been about 25 years. And maybe you guys can help me if you feel like I could use the help like that.
I doubt anyone in our audience has seen that or played this game.
Okay.
But maybe we'll see. And so this was for the ZX Spectrum. So we have
ZX.
Yeah, if you're British, it's ZX, or you learn the British style of English. Yeah. So ZX Spectrum. We have a request a factoid. Maybe you could explain what the ZX Spectrum was.
Oh, so the ZX Spectrum was like a amateur computer system. So the ZX Spectrum was early 80s. So this was before the Apple II, as Ken just found out. And it was like a small, a 48 KB RAM self-contained system with a basic compiler. You could do programming on it. And you could play games, and the games were kind of like this. So this was actually a fairly sophisticated game for the ZX Spectrum. And you take your console and you'd hook it up to a TV and a tape recorder, and then the game would be stored on the cassette tape, and then you'd play the tape. It would take a few minutes to load, and then you'd play. Right?
Yeah. So it would literally read the magnetic tape from a tape player.
That's right.
And that's how it would interpret the game. And so this was one of the first color computers.
That's right. That's right.
So these colors are vibrant, but they were a first. That's pretty fun. Yeah. So this was the UK equivalent to the US Commodore 64.
Right.
And this was huge in the UK and India apparently as well. So yeah, pretty popular gaming system. And the guy doing guy things, I'm not sure that's the factoid you requested, but you learned about the ZX Spectrum, so. So the backstory behind this game is you are Dynamite Dan, and you're playing against Dr. Blitzen. I had to read up on the lore of this game. I needed to know the backstory so I could be invested in the gameplay. And you are fighting against Dr. Blitzen. And so you have to collect dynamite and then blow up something and save somebody.
Which is not going to happen, right?
Definitely counts as a factoid. Thank you, a guy, for the request a factoid, the take a drink, and for showing up. Thank you for joining us again.
Thank you.
So you made it through 7 screens.
Okay, so the goal is to do
So let's pause. Let's
Okay.
start a prediction. We don't have a whole lot of people in the room right now, but how many rooms do you think you're going to make on this one?
You're asking me?
Yep. How many? What's
So I
the
did
over?
7 right now, right?
Yep.
And I just played the game again after 25 years. So if am I going to be playing this for like 15 minutes, you think?
Oh, you'll play this for at least an
Hour?
hour.
Okay, then I say 15 screens. Like I'll
15
double.
screens.
Assuming there are 15 screens in the game. I honestly
I
don't
think there's
remember.
over like 200. So we're going to
Okay.
say greater than 15 or less than 15. And if you hit exactly 15, I'm not sure what happens. So, all right, we're going to throw a prediction up there. So screens are just the number of literal like rooms he goes into. And he made 8 screens there. Will he get greater than 15 or less than 15 on this try? So yeah, spend your internet points. Guy doing guy things. Thank you for redeeming another take a drink.
Okay.
Sachin, cheers. Guy doing guy things. Thank you. Put your predictions in now. Will Sachin get greater than 15 rooms on this next try or less than 15 rooms? Keep in mind, it's been what, 30 years since you played this?
Yeah, pretty close
And you
to.
got 7 the first try, and you're going to propose.
Anybody who says over 15 is probably overestimating my ability, right?
you're biasing the data set. Somebody believe in Sachin. He needs the support.
I'd take the under.
You got one skeptic, no believers yet. Someone
Okay.
greater than 15. Sachin's going to do it on this try. All right, I think you can go. I don't think it's going to bias the data set. So you'll notice that the heads in the corner down here, that's how much energy or life he has left over. So we'll see how far he gets on this round.
I'm gonna start going the other way now.
I love your About Us game description where you were planning on going pro in video games and you gave it up. I don't think there were pros back then. All right, so we've done sufficient. Oh, we got 3 believers and 1 skeptic. You have 20 seconds left. Spend your standard internet units on betting on Sachin. Will he? Oh, Reese's Pieces redeemed. Take a drink. I
Okay.
don't know if you knew, but you were probably getting pretty drunk tonight. Oh,
This is like I gotta keep running right now because this.
yeah.
Whoa. Okay.
Cheers again. Thank you again for stopping by. Non-dairy neutrino believes in you. Polymer's rule also believes in you. So, we got 3 believers and 1 skeptic, so it's on you. With that, I think he's had time to settle in. Feel free to throw your questions in chat. Again, joining me today is Sachin Shanbhag. He is an expert in modeling soft materials, things like DNA, polymers, natural synthetic polymers, proteins, soft materials. I'm trying to describe things that are relatively large from a computational type perspective, and doing things like Monte Carlo simulations plus Bayesian statistics to analyze and describe those materials. So if you have any questions related to those topics, please throw them in chat. So in the water, presumably you're done. No! 12
Oh,
screens.
not bad.
Oh. Option is less than 12. So congratulations, skeptics. I'm sorry all that believed in Sachin. He let you
But
down.
that was not the next game, right? Like that was in the next half an hour.
Oh, in the next half hour? Oh, I didn't
Oh,
know
you
this.
meant the next game?
Yeah.
Oh.
I hope I made that clear. I'm sorry if I screwed you guys out of points.
Oh.
All right. Who has questions for Sachin? While I'm waiting for people to type away, let's start with an easy one.
Okay.
6-year-old Sachin was not like, I'm going to be a, computational chemical engineer. What led you to where you are now?
So I want to say a little bit of interest, a little bit of talent, and lots of accidents, right? Serendipity. So when I grew up in India, where most parents want their kids, the stereotype is actually quite true. They want their kids to be either an engineer or a doctor, right? And my mom was a doctor, which was enough. So I saw that I didn't want to be a doctor because I thought that was, I didn't have it in me. And I liked physics and math, so those were actually the sort of, those are the only reasons why I why I decided, like to pursue math, science, and engineering. In 12th grade, there's like this big test in India that you take, and I happened to be, I was lucky. I mean, I don't say that modest, with modesty, but I went to a decent place, a decent university called IIT, and over there, I was very impressed by my professors, and I thought, maybe I want to be like them. So it was essentially just modeling people. I thought. As I'm sure you think Ken and I are, right? Like impressive people, right? just not video games, right?
No, they've seen you play Dynamite Dan. No one is thinking that right now.
Yeah.
7 rooms later.
Right. Yeah, and then I came. I did my undergrad in chemical engineering, and so the professor I was doing research with thought I would, I should go to grad school, and then he sort of validated essentially what I always, I wanted to believe, that I would make a good professor. And I went to Michigan grad school, and there, I again had a great advisor. Just loved the experience. I didn't want to get out of school, and so that's precisely what I did. I mean, I'm I've never left the ivory tower. I've just gone from one side to the other, really. And so, and then I came to Florida State in 2006.
I mean, it just goes to show you how important your advisor is.
Yeah.
Like, that's something I reflect on advising students. Like, there's things you should do and not do. And
Yep. Yeah.
so you ended up being an engineer anyway.
Yeah, I did. Yeah,
So you fulfilled that goal.
and kind of a doctor too, right? Like, I mean, if you think of PhD as being
Yeah. No.
doctor, like I know it's a fake kind of doctor. But,
No, I refuse to accept that. So our flavor of doctor were doctors when they were still cutting up people in barber shops. So I think we're the real doctors. All right. That's not a competition. Pretend I didn't say that. All right. Non-dairy neutrino has a fun one. What programming language you use most and why? For myself, I'm looking into getting into computational physics, and I prefer Mathematica because it makes more sense to me.
actually, that's an excellent question. So I have sort of two levels of answers, right? So the first level of answer is okay. So let me answer the first question first, which is the language I've used to do my research has actually changed over a period of time, as you can tell. So my first computer was a ZX Spectrum, and so the first language I learned as a kid was BASIC, which is fine, for doing certain kinds of things, but not really for sort of doing sort of science problems, right? The first sort of serious language that I learned to do sort of research was actually Fortran. I know Fortran gets a bad rap in a lot of circles, but and some of that is deserved, right? I mean, it's an old language, right? It's a language from the 60s, right? So early 60s at least. And at that time, it was sort of as being very modern, right? And right, so Fortran was the first language I learned. Eventually, I started.
9 screens.
Yeah. Progress. I don't know.
Yeah.
The average is going up.
The average is going up. The trend is sloping upward.
Yeah. And then I programmed in C and C++ for a fair bit, and I think those are fine languages too. Increasingly, I do a lot of like right now the language I do most of my work in is Python, and largely because Python has like its library set is just a scientific stack. It's so easy to get started doing something. That like you can solve fairly complicated problems. You can get a head start on it fairly easily. So I'd say Python's the language I use the most right now. But the language I'm most excited about is a language I started learning like in the last year called Julia. It's a language that's maybe 7 or 8 years old now, and it's a language that's designed for scientific computing. It's It's actually very fast. Has sort of a very rich library set, and you can do lots of things that you could do with Python. So my suggestion is, if you're going to try, if you know you want to do computational physics or sort of any scientific computing, that may be a language to look at. It may not be like may not be the advice I would have given you 2 years ago, but that's the advice I would give you now. It's a language that's easy to learn. It's a language that's easy to program in. It's a language that has a fairly rich library set, and it's extremely powerful. Like it runs fast. It has a just-in-time compiler, so you can do things fast. Mathematica. I mean, I use Mathematica too. I'll tell you why that's not the sort of why that's not my mother tongue as a language. One is Mathematica is sort of paid software, right? Which is I have nothing against that. I think Mathematica is the best paid software that you could buy. The trouble is, every few years you'll have to buy new Mathematica software. If you want to share your code with somebody else, that other person will also need to buy, some sort of Mathematica software. If you're in a university setting, maybe that's fine because universities often have sort of site-wide licenses. But just from that angle, I feel like I wouldn't hitch myself to just Mathematica. Although it's a fine complement. It's nice to have that as another thing in your arsenal. And in scientific computing, you have to be multilingual anyway. Okay, so yeah.
So Reese's Pieces agrees with you, Julia Hype in the chat, and also at Simulus, who I think it's a EDU streamer that does computer programming related things, also agrees with Julia for science.
Yeah, so I may be sort of I'm not an expert on Julia. I've sort of started learning it last year, but I did write one paper using where I used actual not on Julia but using Julia to sort of get my results. And I actually really like it. I mean, it has Python-like abilities. Things are easy to it's easy to do stuff. Very rich library set, but it's fast. It's faster than Python. Like your for loops, etc., run really fast. I don't know. Are my answers too long? Or,
no, that's a good answer. I mean, clearly people are invested in the topic because that matters. And that's a recent software package.
So the package itself is, I want to say, less than 10 years ago.
Okay.
The language itself, but like a language needs an ecosystem in order to thrive, right? I mean, if you people who use Python, for example, the thing that makes Python powerful is its libraries, right? I often sort of joke, right? I mean, you may have heard the Rudyard Kipling sort of quote, which is, the strength of a wolf is in the pack. I feel like the strength of Python is in its packages, right? I mean, it's really its libraries that it gets its strength from, and Julia is sort of getting there. So I think it took a few years for the ecosystem to sort of develop, but now you can do, like so for example, just an example, one thing that computational scientists do is solve these systems of equations called ordinary differential equations. And Python has a reasonable sort of, basic set, but Julia, I mean, like, I don't know, like, some of the algorithms that are implemented and like, they are actually really good. I mean, so I feel like people who write them are not just software engineers, but also like, people who are really good at programming, etc. Yeah.
So if you stand on the trampoline, you can jump higher and higher, right? Okay. That's how you get that.
Is that how I do it?
I think so. I haven't been able. Yeah, there you go.
Oh, all right.
Worth it. All right. Non-Dairy Neutrino says, awesome answer, thanks. And I definitely agree with your thoughts on Mathematica. So, yeah, excellent. Satisfactory answer. All right. Reese's Pieces wants to know, and I hope I get this one right. What are your thoughts on the pedagogy of programming to start with one of the mother languages to learn the standard techniques from scratch before using languages with fancy libraries and packages? Like,
right,
starting with Fortran,
like Fortran or C.
Yeah.
So it's easy for me to agree because I feel like that just confirms all the priors I have. And
bias.
that's the way I did it, right? Like, so there's sometimes you think just because I learned it this way, this is the way everybody should learn it.
Yeah.
But having said that, sometimes like I think there is value. I don't think everybody should follow the same path. Like if you're like if you're, I don't know, like just take machine learning, for example. Right now, the existing libraries for machine learning are sort of, okay.
Oh, no.
But that's a new high score, right? 410.
Yeah.
Okay.
Dr. Blitzen. Coming out with a laser finger. All right. Yeah, just keep going. It's all nostalgia flashback at this point.
Okay. Yeah. So I do think there is value to learning, especially if you're going to be a serious programmer. I feel like there is value to learning like a Fortran, a C, a Java, where you're doing low-level stuff as well. Maybe even writing some sort of rudimentary libraries yourself. But if you, if your goal is not programming per se, but maybe you're just interested, I don't know, maybe you're a person from an art department who wants to do some sort of neural style transfer type work. Like I wouldn't place the same sort of burden on you. I mean, it's okay to learn a language with a rich library set right away, just so that you can get working right away, right?
So do you require modeling in your classes?
So most of our classes have some element of modeling. So scientific computing or computational science is as a discipline is a relatively new discipline, right? And I like to say it sort of stands on three pillars, right? So one pillar is some sort of a science. It could be like physics, could be chemistry, could be ecology or epidemiology. I mean, that's sort of something in the news, right? So you build models based on your knowledge of some sort of science. And typically these lead to mathematical models. Often, I mean, at least the models that I most often work with are mechanistic models. So, so the underlying equations may be something like Maxwell's equations or Newton's equations or some sort of equation that we, some sort of sets of equations that we understand how they work. Then, right, so the first pillar is a science. The second pillar is mathematics, right? So you have to be able to do mathematical modeling. And then the third pillar is, most of these models are too complicated. You can't solve them analytically. And so you need to sort of be able to, you need to be able to sort of explain that model to a computer, right? And so computing sort of is the essentially software or computing or algorithms is sort of the third pillar. And you need a little bit of all three.
Makes sense. So your department is composed of people that understand modeling and software and apply it to very different problems. So
that's right.
Your seminar series, when people come and talk,
it's
diverse, presumably.
It's very diverse. Like, so if I just try to think about the people in the department, there's like an astrophysicist, there's a geneticist, people who does population genetics. There are people who do, who are like applied math people. There's a couple of people like me who do, materials. It makes for an interesting conversation. We're also sort of I think it's an interesting department in the sense in most traditional departments, like a chemistry department, for instance. I mean, I don't want to sort of, this is not to trivialize, but, sort of broad strokes. You're interested in the same sorts of problems, and you use different techniques to attack the same problem. So somebody may, maybe, I don't know, may have some may have expertise in some methods like neutron scattering. Maybe somebody is a modeler. Maybe somebody does theory. Maybe, right? So you come at the same sort of problem from different angles. Whereas in our department, it's sort of, so the tools are different, the problems are similar. The tools tend to be similar, but the problems are very different. And so that's an interesting dynamic. And this is not, I think it makes for fun conversations with colleagues.
I mean, so usually the people that would present would understand that, right? And they'd introduce
so
the topics.
Right, so you have to make the effort, right?
Yeah. I do not understand these game physics. It's like you got to hit that jump perfectly. Yeah, there you go. Oh, the forks are really intimidating.
Yeah, if anything looks too intimidating, I just run through it.
I mean, that's one of the interesting things because, like, scientific computing, like someone like Wei Yang might fall under that
Yeah,
category given the right
right,
situation, and
right.
so
He
he
used to
does.
be in the department too.
Yeah, so he does like molecular mechanics
Right.
and dynamics of proteins and things, and
That's
it's
exactly right.
modeling
Yeah.
big systems, and
Yeah, I
I
mean, as
guess
a discipline, it's a relatively new discipline, right?
mhm.
I mean, there are not too many departments of computational science or scientific computing in the U.S. And when our department started at FSU here, it was one of the I think it was the first department in the country. Now there are about 10
The first formal scientific computing
scientific computing
department.
department, and it's sort of interesting how new disciplines emerge from old disciplines, right? So
Yeah.
there's almost like this. It's an interesting battle and sort of reconfiguring of sort of lines that happens. I guess I feel like math would probably be most familiar with, like departments which we take for granted now, like statistics or computer science, used to be parts of math departments, right?
Yeah.
Less than a century ago.
Hmm.
And so like how they separate out from a department, and then it takes a passage of time for departments to develop their own culture and their own sort of ways of looking at things and methods of inquiry and stuff like that. I think it's kind of interesting. I think it'll take a few years, but I mean, I really do think that scientific
Ooh,
computing is a
11
discipline in itself.
screens.
11, right? That's
We're
not
on
the
the up and
highest.
up. I mean, that's not just it's not just scientific. It's political. It's financial. It's like starting a new department. It's expensive. You're
Right.
stealing personnel from other departments.
Right.
You're
And
stealing
then
students.
who do you hire? Like when a chemistry department hires a new professor, you're looking for a chemist. You're looking for somebody who was a chemist, who has
Yeah.
a training in chemistry. Whereas if you're looking for somebody in scientific computing, you're looking for somebody who could be in the physics department, could be chemistry, could be biology.
So, what do your job search ads look like?
So again, like I said, there's three pillars, right? So most of our students end up going into companies that specialize in one of these three things. So it could be a standard sort of engineering company, like could be like a Lockheed Martin or like a software company. Yeah, because I mean, some students are actually such skilled programmers that they make excellent software engineers, and software engineering is not an uncommon sort of job that people, students eventually end up getting. And then there's also sort of this business of managing sort of large computer systems, right? And so a lot of students also end up going to things like national labs, where which tend to have sort of longer, which you can do bigger projects that stretch over decades and write software that sort of lasts and lasts and stuff like that. Yeah, so yeah.
Very diverse. All right. A big spooky skeleton wants to know, what is soft matter? I can't think of any polymers that aren't very rigid.
That's very interesting. Yeah, so
So it's a very different definition of soft matter.
right. So, I mean, just to give you sort of some sort. So what we're trying to distinguish here. So hard matter would be matter like metals, and soft matter actually encompasses like a wide variety of matter. So let me sort of let me pose this as a question that I often pose to people who I first thought who were first introduced soft matter. And so in maybe high school you sort of learned that there are three states of matter. There's solid, there's liquid, and there's gas, and maybe there's this couple of more exotic, maybe there's plasma, and maybe there's post-Einstein condensated. But let's say just solids, liquids, and gases, right? And if I tell you what state of matter is ice, you'll say it's a solid. If I say what's water, liquid. What's water vapor? I mean, it's a gas. But then if I ask you what state of matter is, let's say, something like toothpaste, or what state of matter is, I don't know, like foam, shaving foam, or Jello, right? Or mayonnaise. I mean, there's lots of food, lots of cosmetics, where these are materials that can hold their shape for a really long time, like solids do, but they're also very deformable, like liquids are. And so these materials often, like these would be, these are often called complex fluids or soft matter, etc. The sort of more physicsy definition is you can, like the relevant energy scales are of are of order thermal energy, right? So if you change the temperature, if you change the temperature a little bit, you can cause lots of changes in these materials. But they're soft in the sense, you can deform just like toothpaste, foam, or lots of polymers. When they're processed in the molten state. I know polymers that you see eventually, or plastics that you see eventually. They may be very rigid, but a lot of polymer processing is done in the molten state. But they're actually not, strictly speaking, liquids. They're far more akin to something like toothpaste, very gooey. Okay, so that's what soft matter is.
Yeah. That's a good explanation. And so that encompasses like the synthetic polymers, things,
right?
Anything you blow mold, anything you
lots of biological material, lots of colloids. I mean, if you go to your kitchen, or if you like shampoo, anything that you may colloquially sort of call semi-solid would likely be soft matter. And there's stuff that doesn't look like soft matter to the eye, but which over long enough timescales actually does flow.
I was going to say there's a time scale component too.
That's exactly right. Yeah.
There's some glasses that flow and things, and
that's exactly right. Yeah.
I mean, so that's part of the complexity of modeling this, right? So if you have a crystal has a well-defined structure, and that structure maintains for the most part.
Right.
But soft materials, typically they're amorphous, they're random, they move, they change, they're dynamic.
Yep.
So in your modeling, there's an intrinsic temporal component as well.
Yes. There's some randomness. Always. Yep.
It's fun. All right, we're at the 8:30 mark. Anyone that's just joining us, again, joining me today is Sachin Shanbhag. He's an expert in scientific computing, particular in modeling soft materials, chemical engineering background as applied to computer science related calculations. Does things like Monte Carlo simulations as well as Bayesian statistics. So if you have any questions, feel free to throw them in chat. Big Spooky Skeleton has a comment. I'm shocked the massive wheel of cheese wasn't worth more points. I agree.
You can tell I'm so focused. I haven't been. I don't know what causes.
I think they're all worth the same amount of points. Big Spooky Skeletons reminds me of rheology class where we talked about lava flowing like peanut butter or ketchup. Lava, that's a fun one.
Exactly right. Yeah.
It's an unexpected soft material.
Yeah, that is exactly right. Yeah, lava is.
So that's a good question. Like, at what point do you draw a line between soft material and liquid?
It's a blurry line, right? Yeah. So, I mean, you may think I'm avoiding the question, but it's sort of generalizing the question, right? So, just like you can change temperature, you can have a material that's a solid. You change the temperature, the same material becomes a liquid. The very, in sort of almost the same manner, you can have a material which you interrogate at fast enough timescales. Mm-hmm. So, if you interrogate it at fast enough timescales, so if you sort of, if you try to, right, so it may behave like a solid. If you sort of like to, you can smash certain things and they'll sort of shatter apart. But if you let them sit for a long time, they will flow. In fact, in rheology, I mean, there is this classic. There is this, in lots of sciences, there are these dimensionless numbers, right? In a lot of modeling, where it's typically the ratio of two things. But there's this number called the Deborah number, which effectively says I can't go down, can I?
Yeah, you should be able to. It might be W. Maybe try spacebar might bring you down. Or arrow plus spacebar.
Maybe I gotta go on the boat, and maybe it's one way. Maybe I can only come up.
Oh, you gotta drop on it?
Yeah.
That's brutal. Dimensionless parameters.
Yeah, so there's this parameter called I didn't mean to. They call it Deborah number, and so which effectively measures how solid-like or liquid-like a material is. So it's the ratio of the intrinsic timescale of the material divided by the timescale of the deformation. Right. So if you are you sort of doing things fast, or are you sort of slowly smushing things around? And the interesting part is the label Deborah. So there was no scientist called. I mean, maybe there was a scientist called Deborah, but that's not the scientist. This number is named after. The number is named after. It's this biblical reference. So apparently, I haven't read the Bible, but apparently. There's in the book of Judges, there's this Deborah, this prophet Deborah who says the mountains flowed before the Lords or something like that. And that's where it comes from, right? Because the mountain looks very solid-like, right? A mountain you think is a solid, but on really long enough timescales, geological timescales, they flow.
Close,
right?
yeah.
Know they flow.
That is amazing.
And so the question of whether something is a solid or a liquid is. One way of asking it, how patient are you?
Yeah,
right?
It's literally a biblical question.
Right. It really is, right? So the
epistemological.
Right.
That is amazing. That would have been a great factoid. That's where that number comes from.
Yeah.
Or where the
I
name
had
for
a
the
factoid,
number.
sort of. There's that. I don't know. Do you want to do? Oh
No. We'll wait for request to factoid, but that one would have been perfect.
Like one of the questions there.
Yeah.
Sort of refers to.
All right, which one? Oh, this one?
Yeah.
All right, we're going to throw up a prediction. It is time. Sachin's requested one. If you're not following us, click follow, and you'll get 300 standard internet units to spend on predicting things and requesting factoids and requesting we take a drink. But for now, I'm going to pop up a question that Sachin has requested. All right.
You want to do the number 3 first?
Okay. This one? Wait. Which one? Whoa, sorry. I got a copy and paste there. There we go. All right. So we're going to throw a prediction up right now. You guys have 2 minutes. The question is, what is the longest running experiment? At least formally documented experiment. Obviously, climate change and global warming and whatnot are pretty substantial experiments. And mountains. But the longest running formally documented experiment, how long is it? Is it greater than 60 years or less than 60 years? Keep in mind, this could transcend any discipline. This could be genetics research. This could be physics. This could be chemistry. What is the world record for longest running experiment? Is it greater than 60 years or less than 60 years? Again, if you're not following, click the follow button right now. You'll get your 300 standard internet units and gamble them away on what the longest running experiment is. So that's a fun question. Yeah. I actually teach this in my class, so
you do. So you knew the answer.
I did know the answer to this one, actually. If that's a hint for anyone, it's going to bias it one way or another. It's biasing heavily towards greater than 60 years.
Yeah.
Anyone else? It's there less than 60 years. Again, this is formalized. This is a published study.
Right.
It's been. Oh wow, you got to walk with the boat? What kind of messed up physics is this?
That's the only way to get to that dynamite, right? And then avoid that.
You got to the boat after all that battle, and then we're shot. This game is so unrealistic. I demand a refund. Time machine and a refund. All right, longest running experiment. Quick, 20 seconds. Everyone has guessed greater than 60 years. Someone be brave. Put 10 standard internet units towards less than 60 years and bias the outcome in your favor. Maybe not the answer, but at least the statistics. We got everyone is betting greater than 60 years.
Social proof, huh?
Exactly. Evidence through statistics. All right, closing 3, 2, 1. Everyone bet greater than 60 years. Sachin, what is the answer?
So the answer is less than six. No, I'm just kidding.
Cruel.
No, so the answer is it's
Greater than
it's almost
60
100 years. It's greater
Yeah.
than 60. It's
Yeah.
greater than 60. Almost 100 years old.
How close to a?
I mean, I wrote this down. So the experiment was started. It's called the pitch drop experiment. And in fact, there's a live. I mean, if you Google the pitch drop experiment and look for a live stream, it's an experiment that you can watch as it is being performed, right? And
Experiment is a generous descriptor.
right. So the experiment itself is it's actually it's a rheology experiment, right? And sort of ties to what we were talking about sort of the last 10 or 15 minutes. So this guy, Professor Parnell at the University of Queensland, in 1927 took a bunch of pitch. So pitch is essentially something you get from tar, from processing tar.
What you repair cracks in the road with sometimes.
Right. It was also used for waterproofing boats once upon a time. So it's this sort of really thick, and it's so thick that if you take a hammer and you hit it, it's brittle. You can shatter it. And so he took a bunch of this pitch and stuck it in the funnel. I mean, he blocked the sort of the stem of the funnel, so I mean, it's like a rock. And then he heated it and let it settle for 3 years before starting the experiment. And at the end of 3 years, once sort of the pitch had settled in, he
settled in and cooled. Took a really long to cool.
Settled in and cooled. He cut the stem, and the observation really is how many drops fall off. Right, it took 8 years for the first drop to fall off. And like I said, so 1927, 2021. So I don't know what month, but let's say something like over 90 years.
Yeah.
9 drops have fallen so far. So it's like almost one a decade. And if I'm not mistaken, the 9th drop was almost a mistake. So after 8 drops, the cup sort of underneath the funnel got full.
Yep.
And while trying to sort of empty that cup, somebody sort of shook the experiment. So it's kind of, it's no longer a perfectly controlled experiment anymore.
It wasn't a perfectly controlled experiment either way.
But it's, it's too much has gone in for to restart that again.
They moved it several times. Temperatures fluctuate. It's kind of an experiment in the loosest sense. But yeah, I just put a link in chat called the 10th Watch, which is the live stream where you can watch tar pitch not move on the screen at all. What's super tragic about the experiment is the founder of it, Parnell, right?
Yeah.
He never saw
a drop fall.
No,
he died
didn't.
before the first.
So he died. They had a video set up to capture one, but something went wrong and they missed it. So he actually passed
missed the
away.
first drop.
Yeah, so he died before getting to see any of the drops fall. Because it's going to happen at a random time, right? You have a 10-year interval plus or minus
The Poisson process.
months and months. Texas Space Agency, welcome back. So yeah, that's the 100-year, almost 100-year experiment. That's 95 years now.
Yeah.
So we're coming up on the 100th anniversary, and it's something like 10 years till the next burst of pitch drop.
Yeah, I think the next one's expected sometime in the 2020s.
Yeah, and so the thing, what's interesting is the rate actually slows because the mass of the pitch actually changes over time. So it's like it's a diminishing returns graph if you actually look at it.
Right.
So yeah. Longest running experiment. So no one got a payout because everyone said greater than 60 years.
It's a bummer. It was a badly set up question.
I mean, or everyone
Maybe
knew
we should have
about
done
it.
like 200.
But I talk about this in class when I talk about pitch draw, or I talk about viscosity. Then that's a super viscous material.
And so the viscosity of pitch is 100 billion times more than that of water. So just for reference, the viscosity of honey is between 1,000 to, let's say 5,000 times the viscosity of water. So this is nearly 1 trillion times more viscous than water.
Texas Space Agency, is the pitch drop isolated from earthquakes or tremors? I don't know where you got the pitch drop. It's probably
if they control for temperature, that's like that's big enough.
Yeah.
But I think the sentiment's right. If you're running a really long experiment, the kinds of things you need to worry about sort of change, right?
Yeah. But I mean, the crazy thing is, at this point, we could probably model that better than the actual experiment,
That's
right?
probably
This
right.
is more
Yeah.
predictable than,
Yeah.
yeah. Related to that, we have a few different comments. I'll go back to that. Reese's Pieces said, "Do you count the Oxford electric bell as an experiment?"
Well, I don't know this experiment.
I think
What
I've
is
heard
it?
of this before. It's a bell that was like scheduled to ring, and it's been nonstop. Let me see if I can look it up. Oxford electric bell. I don't know if that does count experiment. Depends on how you want to word it. It's an experiment of electric bell that was set up in 1840 and has run continuously ever since. It was one of the first pieces purchased for a collection apparatus of clergyman Roger Walker. So this is just a bell that's been running indefinitely. Presumably this is run by some kind of
Wow,
photovoltaic
electric,
stack.
right? So I think
Yeah.
that the fact that it's electric is more impressive.
Yeah, so it's just a
From
chemical battery that's
1850.
been running forever.
So Ken, you probably know that. Like, what do you know when the first electric battery or
Oh,
like,
that would have been early
like Volta,
1800s,
right? So maybe
right?
1750s or something. Yeah.
I mean, there's examples of batteries where they were putting like copper and like tin, two different metals together with salts between them and getting certain behaviors.
Yeah, but like to do work, right? Like this is
Yeah,
doing
to actually do
work.
something useful. First practical battery was 1836. So
that maybe that is what's used in that, right?
so 4 years later, they were like, I need to
Wow.
run a bell indefinitely for the end of time. They set up the Oxford bell. I don't know if that counts as an experiment. There's a few other examples of that. There's another continuous long-running light bulb, but yeah, really fun experiment.
Yeah. A light bulb which still exists. It's not gone off.
There was one that was continuously running for a long time. I don't remember the
Wow.
actual number
I
associated
thought
with
like
it.
if it's like I thought the early light bulbs lasted for like a few years, right? Like
Yeah.
the carbon filament.
I don't think it's quite 1800s, but there's a long-running one somewhere. Yeah, Jason thinking, I remember teaching about intermolecular forces and using pitch drop. It's exactly in every Gen Chem textbook. Like there's the example and there's the picture of it. And
Interesting.
so
It's
when-
one of
when
those things that I thought I knew, but not too many other people
So
knew.
when I
It's kinda-
teach Gen Chem and I'm giving them a test, I actually put the pitch drop experiment up on the screen because it has a clock on it. So that's they can watch in real time and cheat off
have
of it
you
if they
so
want.
there's a similar experiment that I show people. Have you seen that experiment where they actually do what Galileo is supposed to have done, which is drop a ball and a feather at the same time?
Yeah,
in
yeah.
vacuum? Have you seen that?
Yeah. What about the viscosity of the oil of a clapped out old Ford? Probably pretty close. It's our pitch experiment.
Is that a pitch?
Oxford electric bell. All right, let's get back to. Didn't they form a rudimentary battery in the Ark of the Covenant to shock Pilgrim? I can neither confirm nor deny.
Nor deny, right?
Democracy is the longest running experiment.
Ah,
Yeah, that's
I mean,
fun.
that maybe we're being
Yeah, we're too narrow in our
yeah,
definition
we're
of
just saying
experiment.
natural sciences, right? I mean, maybe you should, if you think sociological or
It might be. All right. So back to the science question. So for your kind of dedicated scientific computing work, do you use something like a cluster or even distributed computer or a personal computer? What do you use?
so all of the above, right? So it depends on the I forgot. Okay, so all of the above. It sort of depends on the problem at hand. And so any there are problems that I can solve on my laptop. There are problems that I need sort of a cluster set national labs for. FSU has a fairly decent HPC center too. Interestingly, I mean now increasingly like GPUs can do lots of oops, they're not particularly expensive to buy, and you can do like fairly intensive compute work on a GPU that you could buy and put next to your desktop, right? Wow, this is a screen I haven't been to before.
Can you go through there?
I have no idea.
I don't think so.
Like I feel like I'm going to get past these three and then find out that I can go no further, right?
Well, you can't even get through those guys without dying, right?
Yeah, like Yeah, I
This game, the boat physics.
okay.
Oof.
Phew.
So if you fall in the water, are you dead?
I'm done.
That's
I think
officially
I'm
done.
done.
Okay.
I can't swim. It's like,
Texas Space Agency following up on the Ark of the Covenant and the making batteries. Unfortunately, while I'm searching for electric holy relics, I'm just finding theology stuff and ancient alien type stuff. So not founded in scientific or historical
I
background.
think what's interesting is, so the field that I feel like I wear many hats, but one of the hats I wear is, I call myself a rheologist at times. And for the longest time, even now, when I use a computer, I use like Word to write rheology. It'll often say theology, so maybe that's a sign, right? It'll try to autocorrect. The G means.
Just on faith. Non-dairy neutrino had a follow-up on that question. I'm reminded of my own research and seeing how some astronomers go about by leaving a single desktop machine processing for however long it takes.
Yeah, however long it takes, right? Yeah, and so to just finish up on that, I mean, what's for a long time, this Moore's law just meant there was only one way in which you could do bigger and bigger problems. But now it's now that you sort of practically seem to have run out of that, and like you're doing multi-cores, GPUs, sort of different architectures. Things have become interesting again, right? So you can now particular problems you can now sort of approach in sort of ways that in new ways, and which makes a job for somebody like me sort of interesting again, right? Like GPUs are actually really good for solving certain types of problems, like linear algebra problems. I mean, they're great. They're some materials modeling, like molecular dynamics. I know you can use GPUs to accelerate those kinds of code really fast. But a common friend of ours, Eugene, for example, who works in quantum codes, finds that they're not particular. I mean, they do improve speeds for the types of quantum calculations he does, but not that much, right? So he gets like a factor of 5 or a factor of 10 improvement, not the several orders of magnitude that you can get for some of the problems. Yeah. High score.
15 screens, there it is. So you're 52 minutes in. So you would have lost that bet either way. That's awesome. We do a few more minutes because we're going to do the sequel soon.
Okay.
Yeah. All right. Reese's Pieces has a question. What types of questions are closely related to your current work but are still very difficult to answer? So what are the holy grails of problem solving in your discipline?
Yeah. So I mean, well, I guess this is a problem. Not just in what I'm interested in, but maybe there's lots of it's a modeling question in general, and the modeling need not be materials modeling, right? So, and it's something that I've spent some time thinking about. But I don't have I have no sort of deep insight or foresight. I don't know what's coming in the future. Which is basically or how much can AI or machine learning supplant sort of careful modeling work that
Wait,
we can do.
Did you
right?
were you invincible there for a little
Yeah,
bit?
so if you eat that deodorant thing, I don't know why, or maybe it's a spray. I don't know if it's a deodorant.
That was the Dynamite Dan equivalent of a star, and you got super defense, like infinite whatever. That's awesome. That's what the flashing was. Sorry to interrupt. Anyway.
Right. So I feel like the interesting. I mean, one question that so right now the way most of us build our models is, like we appeal to some. So let's say physics is the easiest to describe, right? Because there's a few universal physics laws, like maybe Maxwell's equations or let's say Newton's equations, which my guess is many people would be familiar. You can get a lot of mileage just from F equals ma, right? So the Newton's second law underpins a lot of materials research. So what people call molecular dynamics is really just applying Newton's laws to a bunch of atoms, and then the forces between them are not gravitational forces like Newton's gravitational forces, but interatomic potentials, right? So which I mean, that how you get them is a different story. But once you have them, you essentially just you just press play and let Newton, like just integrate Newton's equations, right? And so right now the most sort of common sort of mechanistic modeling paradigm is you have an input. So let's just stick with an atom, with a system, right? So let's say I want to study, let's say the density of some material. Let's just say water, using a computer. I mean, I know I could measure it in a wet lab, but let's say I want to sort of do a computer simulation and figure this out. I would take a bunch of water molecules, stick them in a box on my computer, and just run Newton's equations on them. Just press play, and then the computer does the integration of the equations, and then eventually I as they do these trajectories, and you can use something called statistical mechanics to take these trajectories and convert it into sort of information that you seek, something like the density. Okay, so you have this input that you put in. There's a model that you understand, but you haven't really evaluated the model. You stick it in, the model runs, and you get the output, and you get your answer. But there are lots of cases where we don't know the model, right? Where we maybe we molecular dynamics is a place where we maybe know what the appropriate model to solve is. But in cases where we don't know what the true model is, but if let's say we have lots of observations, you could think of this as something similar to let's say handwriting recognition or recognizing sort of like when you in your Google Photos, you say look for sunsets, and it looks for all sunsets. Mm-hmm. So it's built an internal representation or an internal model of what a sunset is, right? Now the model itself is probably very complicated, right? So the way Google built that model is it took maybe there's lots of people who actually tagged a lot of pictures of sunsets, and then it did a lot of this machine learning, maybe built like a neural network or some sort of a model, and then next time somebody gives a picture that's not, so you've trained the model. You really don't understand the model because the model is like just a bunch of weights and links and stuff like that. But you can run the model in a predictive mode. So if you give it a new picture, it can tell whether it's a sunset or not. Or maybe it can do even better. Maybe it can tell you whether it's sunrise or afternoon or sunset and stuff like that, right? So that seems to have worked quite well for image detection, for face detection, even autonomous driving, right? So the car is building a model of the world, and it's a fairly complicated model. The question is, can we do the same with physical systems? How much of that machinery can we import into science? And I used to be a bigger skeptic of this before than I am right now. Although I have to admit, I'm still somewhat skeptical. And my skepticism really stems from not being able to sort of parse the model. So maybe the computer has learned, but what have I learned? Because our models, we understand the world using some primitives, right? We understand a few basic laws. And whatever the computer has learned, we want to sort of project that in terms of the laws we understand, right? Like I know if I throw a ball up, it will fall down, and I know why that happens. And whatever representation, whatever model the computer is learning, I would like to be able to understand through stuff stuff I can parse. So primitives that I understand. And I for a long time I was very skeptical of a computer's ability to do that. But I don't know this literature as well as I'm sort of starting to learn this. That there is this literature where you can do something called scientific machine learning, where you can actually just write your equations like you would, and the parts that you do not understand, just those parts you let the model learn. So something like trying to find the density of water. Maybe I know Newton's laws. I know those are the appropriate set of equations to solve and stuff like that. But maybe I don't know what language two water molecules speak. So I don't know the interatomic potential. I could just take lots of data and just learn that. This particular problem seems somewhat impractical. Maybe this is not the best way of going about it. But you can essentially you can constrain the model sufficiently so that whatever the machine learns, has to be, sort of false in the parcel where you can understand what the answer is or looks like. So I feel like that, this essentially this interface of artificial learning and or machine learning and sort of traditional sort of modeling, sort of mechanistic law-based modeling. I think that's an interesting area, and I partly say that because I think that is interesting to me, but I also think that has sort of larger sort of consequences and impacts. It's been so successful for a certain type of problems.
All right, Dynamite Dan 2.
Sure.
Good. We're on to the sequel, ladies and gentlemen. Dr. Blitzen is back in the sequel. And Sachin, you have not played this one before.
I have not.
This is a first. It's pretty much the same game with slightly better graphics.
Slightly.
But I mean, the machine learning thing, that's a hot topic across every discipline, right? That's one of my new loves. I don't work in the area, but I love the concept behind it.
Yeah.
Texas Space Agency had a comment about, isn't there some machine learning that does nothing but identify hot dogs and
I wouldn't be surprised, right?
But I mean, like in terms of what you're saying, so machine learning basically takes a huge data set, fits it with a polynomial, and finds some trend in said data set. And like what you're saying is it's not based on fundamental principles. It's just creating an equation that describes the data.
Right.
And so, I mean, that equation might be a fundamental principle, but we don't know.
It could be,
necessarily, right?
And we don't know if that's the simplest way of representing that it's taken that form because we trained a network with that form. We don't know if that's the simplest way to represent that.
Well, one of the things I really like about machine learning is it can find the outlier data sets, right? If you have a parameter space and you have that polynomial and you find an outlier, that's where most new scientific discovery comes from. Yep. So even if the polynomial itself isn't a new theory or fundamental law, it might show you a gaping hole in our understanding of something. So I love the area
with data, right? And so this is, I mean, what you just said sort of is like the role of outliers in science, right? And this is actually particularly interesting because when I do a lot of modeling, so I work with a lot of math, and I mean I don't do too many theorems, math theorems, etc. But there are people who work in adjacent areas who do that. So I sort of read the literature every once in a while. So if you think about like this math, even applied math and statistics, the modes of inquiry and the weight that is placed on outliers it's almost diametrically opposite. And you think that's so in statistics, right? One outlier may mean nothing, right? So maybe you had an uncle who smoked like a pack of cigarettes every day and lived to 100 and like had a very healthy life, etc. Means nothing. One anecdote doesn't mean anything. Whereas in math, like especially in like pure math, one counterexample can that is all you need.
Everything.
Like one counterexample is enough. And also in math you can prove or disprove things. In statistics, that's kind of hard, right? You can't, like, it's hard to prove or disprove like lots of things, right? Like lots of things, which makes it interesting, but also sort of problematic, right? Okay, so I go.
All right, it's time for Dynamite Dan 2, the sequel, which was rated by Crash Magazine as Platformer of the Year in 1983.
Wow, 1983, right?
It's hyped. This game was the forefront.
At one point in time.
Speaking of gaming, Texas Space Agency says, have you seen the machine learning that will use a capture card and a controller input to detect to undetectably cheat in any first-person shooter game? It is completely standalone and detects player movements and learns to play the game faster than any human could. I mean, yeah, makes sense.
Yeah.
I mean, I stopped playing chess when Kasparov got beat by Deep Blue. It was one of those things, like, I still like the game, but it was like an inflection point in my existence, because it was like, they're better than us, right? Yeah. And it's only a matter of time before.
I mean, they're better in one way, right?
Yeah, exactly.
Yeah.
So yeah, same thing with.
So what do you think of? Maybe I should ask you, Ken. Like, do you think? Like, what about this general intelligence?
Oh man.
And computers with you?
I'm terrified and excited, but I mentally map out who in my department would get replaced first by a machine learning algorithm. Like which sets of expertise can you automate, like if your job is an Excel spreadsheet, you can be replaced by a macro, right? Like, but if your job is encyclopedic knowledge, computers are going to beat you at that, right? So it's something I've thought about a lot. Like, what is my unique contribution? And still some degree of creativity, but that's
Yeah.
not to say machine learning can't do that.
No, it's just, I mean, maybe sort of the broader question is what sort of jobs, like jobs that when things are sort of relatively sort of stable and safe. I guess, like most jobs are not, right? I mean,
Yeah.
maybe high touch jobs. Like if you're a nurse, I think that's that may be something that.
Yeah, and people will often like counter with like creativity, like art and music. But there's a machine learning algorithm that's taken all of Beethoven's works and creates a new Beethoven score.
Right.
And it's
if you can't tell,
exactly.
It like passes some sort of a Turing test.
Yeah, exactly. The Turing test of Beethoven music. Like, is it truly unique? Is it useful enough? Like, I mean, it's terrifying, but it's amazing.
Yeah.
But I mean, for a century now, we've been promised that new technology developments would make our lives easier.
Right.
But that hasn't happened.
I mean, they have in some ways, right?
Yeah.
I
mean, like foraging for food has gone down, but
right.
also
No, but
we're
also
still
like I don't know, like communication. I mean, you can video chat anywhere across the globe for practically free. I mean that's you or just being able to hail a taxi from your cell phone, right? I mean,
no, it's true. But like our work week has gotten longer.
Right.
Like the time we spend, the
well, I think it's made of. I don't know. Like so the first time you did any research, how did you go about finding, like, what was the process? Like, I grew up in India, so my experience was different, but I'm just curious. So how did you go about finding, like, a journal article? What was that? Like, walk me through. Like, how did you, so let's say you want this paper.
I started real research in 2004. And I think by that point...
Oh, okay. You're really young, so you've been spoiled.
I don't know about really young, but that was my first like real summer research experience. Would have been 2003,
so the computers were
2004.
around at that
Yeah. So SciFinder was still reasonable.
Okay.
But yeah, prior to that, I mean, it's...
So I like, the first time I sort of did any sort of anything that sort of bordered on research was 1997, right? And so the internet, I mean, we had internet at our university, but it was, like the resources that, I mean, the ecosystem around it wasn't developed. And so the way you looked for, let's say you were interested in a certain problem, the way you sort of went about, so there'd be these compact discs in the library, some sort of an archive. You do your searching, but the searching would be off of that compact disc. And then all that disc would give you essentially locations of these journals, and then you had to sort of walk. It would take forever to sort of locate one of these journals, and then you photocopy them.
Yep.
And then
I do remember that.
Okay, so you actually
like no, I remember high school. Like so I'm probably the last I wouldn't say generation, but age demographic that remembers life pre-internet.
Okay,
but it would transit.
Right. So I mean, so if you just think about, I mean, so it would take I don't know, like a day or an afternoon just to sort of collect materials that you wanted to read over the next week, right? Whereas now you just go bang, 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 and like you can, you're sitting at your desktop and you've sort of figured out. I mean, it's hard. I don't know. Like I feel optimistic in certain ways, but I share your pessimism in a certain way. I mean, like just look at COVID, right? I mean that sort of exposed the best of science and the worst of. I mean, not the worst of science, but the worst of everyone else to science, right?
Yeah.
I mean, who would have thought we could have gotten a vaccine? And like I hadn't. Like if you asked me if you did this prediction game, like a betting game, I would have said 1.5 to 2 years. I mean, not knowing much. I mean, admittedly, I don't know much about sort of vaccine science and stuff. But I don't know what the previous record for a vaccine
No, it was amazing turnaround.
And the threshold, the safety threshold for a vaccine like this has to have been higher, right? Because they were going to essentially, you really want to vaccinate everybody on Earth, which means sort of like a weird side effect that affects a fair number of people is important to know. And these vaccine studies are paused so many times probably because of something like that.
Yeah.
But that was just amazing.
Imagine the class action lawsuit for
Right.
like
Yeah. And
a
then
billion people.
So you have that on the one side. You have this amazing, and then you have this whole science communication sort of. I mean, like every issue became tribal, right? Which was, I mean, I hope that's not a blueprint for problems in the future, right? Like we're going to have many of them. I hope that's not.
Yeah.
Because there's not going to be a silver bullet for, like, there may not be a silver bullet for many of
We'll
the
see how
other
it
problems.
unfolds. Yeah. Texas Space Agency, congratulations on the paper, and you get to graduate, which is amazing. And yes, reviewer number 3 is always a problem, assuming you get 3, not 2 or 4. But yeah, no, there's something. Like I'm not a fan of pomp and circumstance and just like tradition for the sake of tradition, but like the hooding for getting a PhD, like that degree, like that is a legacy that goes back 1,000 years. Like I was hooded by my advisor, they by theirs, so on and so forth. Like, no, it's a fraternity. Like those degrees, they're undersold and under conveyed because they've become, I don't know, relatively common, but it's not something to scoff at, right? So again,
Like
congratulations.
Right?
Yeah, on the paper and graduating as well. Graduating in August. So if you can walk and get, if you're doing a PhD, get hooded. If you're doing the master's, go through the ceremony.
Yeah.
It's an awesome experience.
I know.
Depending on who your speaker is.
That doesn't matter in a certain way, right?
All right. So I missed one. A big spooky skeleton requested a factoid.
Oh.
Do you have a factoid bomb drop on the audience?
Okay. I showed a couple. Yeah, so I mean, I like this. I think maybe this is actually particularly relevant because of what we were talking about right now, which is COVID, right? So and then also it ties in to my favorite algorithm, which is something called Markov chain Monte Carlo. It's called MCMC, for short. And it's an algorithm that's pervasive in science and engineering and finance. I mean, it's all like everywhere, right? The first paper on MCMC had 2 women on it, and both of them, wrote the software or the code that implemented MCMC. So one of them was Augusta Teller, who wrote the first draft of the paper. So that was like the beta version. And then this other lady, her name was Ariana Rosenbluth. She wrote the sort of the final version. And you can think of what she wrote as maybe the first full implementation of MCMC, right? So she wrote that, and she was like a total badass, right? So she got her PhD at age 22, which is the age most people get their undergrad degrees, right? So sort of fairly, sort of really fast, in physics from Harvard University. And then she wrote the first full MCMC implementation on Maniac 1. She was also a champion fencer. She was like, if I'm remembering right. So she was she won. I don't understand fencing enough, but like I think she was the men's and women's champion in the state of Texas when she was in the university. She was going to represent the US for the Olympics as well, but the 44 Olympics got canceled because of the war, and then the 48 Olympics, I think she didn't. I mean, she couldn't travel because of finances or something like that. And sort of the connection to COVID is she actually lived a really long life. She passed away last year, 2020.
Oh wow!
From COVID.
So when did that paper come out? That was
the paper
1940.
is early 1950s.
1950s.
And she must have been. She was 22. So I think like about 90. She lived somewhere around 90. Right?
Wow. So that's not the first Monte Carlo, but that's the first Markov.
Right. But the first computer implementation
of
MCMC that we know of, right? Because the Monte Carlo method, using computers to solve, sort of science problems. Actually, the origin of that is during sort of the Manhattan Project, and so this guy Ulam and von Neumann and there's a bunch of people who we know sort of were toying around with that, but since it was a secret project, there's no sort of like we don't know if, like there's no scientific paper that sort of documents that.
I mean, that's fair. Nothing, like I tell my students this, you can do the best science in the world, but until you publish it for public release,
Right.
it doesn't exist. Unless you're, I mean, solving a problem. Obviously that matters, but
And sometimes publishing is not enough too, right? You've heard of what's that law? Stiglitz law of eponymity. Have you heard of that?
I'm not familiar with
So
that.
that's so maybe you should Google that up. But it's this law which says that no famous law is named after its true originator. Stiglitz, Stiglitz, I think. And even Stiglitz's law is not named after Stiglitz. Like I think there's some sort of recursion that happens there.
Stiglitz
And there's
law.
lots of examples on the Wikipedia page, which
Stiglitz law. I'm not finding.
or just to do law of EPO. Yeah, Stigler, maybe Stigler.
Stigler's
Yeah,
law.
yeah,
There we
that
go.
seems right.
That's amazing. All right, we're gonna throw it in chat right here. Stigler's law. There we go.
Yeah, they have some sort of a list.
No
towards the end.
scientific discovery is named after its original discoverer. That's interesting.
I think it's an extreme statement.
Yeah, I was gonna say, like Moore's law is named after Moore. He's the one that published it first. I don't know if he came up with it, but yeah, that's pretty fun. Yeah, but didn't Newton invent calculus at like age 23? I think he was 26 when Newton came up with
Is that right?
calculus.
Yeah.
It's really young.
I think I mean, I don't know. I feel like Newton was truly special.
Yeah,
I
that was
mean,
an exceptional. And Bragg's son, Nobel Prize in chemistry for X-ray diffraction. He was like 20 something.
Yeah, I don't know if she was the youngest necessarily. I just think it was young.
Youngest Nobel laureate.
Isn't there somebody who won a Nobel? Oh yeah,
Peace
maybe.
Prize. Yeah, Malala won.
Yeah.
Prior to her. Yeah, so Lawrence Bragg, and then his father came up with X-ray diffraction or some of the early work in X-ray diffraction. So he won at the age of 25 with his father.
Was that before his PhD or after?
I'm assuming it's after, because we're talking 1915. So yeah, that was pretty long age. All right, let me catch up. Adam Savage once said something like, "The difference between science and screwing around is documentation and analysis." That's fair. Keep your lab notebook. That matters. All right. We got a question from Reese's Pieces. Time to get controversial. What are your opinions on quantum computing?
Oh.
Do you have opinions on quantum computing? If so,
I
what are
don't have informed opinions. I just know that even if a viable quantum computer became available tomorrow, and it was... So, I mean, this is a very selfish answer. I don't think it'll change the kinds of questions. It'll radically change the types of questions that I'll be able to answer, right? So, quantum computing's really useful for certain types of scientific questions. Of course, it has larger societal ramifications because I think the big thing is you can break passwords sort of much easier with like essentially you can just explore lots of different combinations much better. I right. So that is clearly important. But what would that enable? Like the kinds of scientific, so the people who do quantum mechanical calculations, I think they will be helped. There are other kinds of problems which lend themselves to be sort of nicely solved with quantum computers, but not all problems fit that mold. It's kind of like GPUs too, right? Like GPUs are particularly good if you want to solve problems that have certain features or properties,
like linear equations and
where you can send lots of data together and the operations are done sort of relatively tightly and you can pipeline that out. If you if you want to sort of CPUs are may not be as good as GPUs, but they may be better than GPUs for certain types of problems, right? So yeah, so I don't have a sort of a super informed opinion. I
Yeah.
don't know. Like, do you know?
I know that's
Yeah.
beyond me. Like, quantum information sciences in general is so big right now. Like, I'm
Right.
looking into how I can contribute to that field. I'd also get money from that.
Yeah.
But yeah, I can't make an educated decision. So yeah, Texas Space Agency followed up with what sorts of questions, problems are well suited for quantum mechanics, and I don't think either of us can answer that. Eugene DePrince might be a good.
Yeah. Yeah.
Yeah.
I think if you want to okay, this is like a very high level answer. So if you ask any follow up question, I won't be able to answer.
No follow-ups.
Yeah, no follow-ups, right? So, but if you have a question that needs to explore lots of branches to get, wants to explore lots of different possibilities, and then so something like optimization, right? So if you have a function and you want, like a complicated function, and you want to find the point at which it's a minimum, you want to sort of do lots of complicated search and sort of branch out. I have a feeling that a quantum computer will be helpful for that. So quantum mechanical problems, which actually are problems of, they're essentially, you're trying to explore lots of different states
Yeah.
that system could be
Probabilistic
in, and then
outcomes,
take
right.
sort of means and averages of that to get to assign probabilities. That's a natural fit. Yeah. So right. So that's the extent to which I can say anything
Sounds good.
semi-legible.
All right, we are due for another prediction. Which one do you want to do?
Let's do maybe number 2.
This one? All right. All right. We're going to throw another prediction up right now. We'll see how this one goes. It's interesting. So we're jumping to polymer chemistry, polymer engineering. In particular, Goodyear and the Goodyear tires. So the Goodyear company, is it named after Charles Goodyear? As in Charles Goodyear, sorry, not named after, but did Charles Goodyear start the namesake company? Did Charles Goodyear start the Goodyear company? True or false? Throw your comments in there, or throw your predictions in there now. Again, if you're not following, click the follow button. Get your 300 standard internet units that you can bet on whether Charles Goodyear started the namesake company. It's kind of a history factoid.
Yeah.
We'll see. Oh man, we got 3 falses already and 0 trues.
Oh, goodness. People are doing game theory, right?
They're gaming the system based on the nature of the question. That is a distinct possibility.
Yeah, I should just do like straight questions,
Straightforward ones.
Yeah.
Oh no, we got one on the true side. 2 people on the true side betting the numbers. Awesome. We have some competitive betting. So Charles Goodyear, again, very important figure in history, but did they start the company that is actually known as Goodyear now? I think it's known as Goodyear Tire.
Goodyear Tire and Rubber Company.
Yeah, Tire and Rubber Company now. But again, throw your predictions in there right now. All right, so completely unrelated to that, I'm going to throw a question at you. What's your favorite equation?
I have a feeling this is super popular.
Is it? We'll see.
So I almost don't want to pick it.
No, pick it.
But
What's your honest answer?
my honest answer is Euler's equation, right?
Euler's equation. That is 3 of my guests have picked Euler's equation.
Like I think there's a certain aesthetic beauty in that, and the brevity, right? I think it sort of ticks too many.
That is the exact answer that
Yeah.
others give. It's the cleanness, it's the elegance, it's the universal applicability.
Yeah, and its usefulness, right? I mean, it's just like so Euler's equation, for those of you who might not know, is essentially says E, which is the exponential 2.73, the number E raised to I. So in its most general form, it's E to the power of IX is equal to cosine of X plus I times sine of X, where I is this, I is the square root of -1. And in its special case, which is actually even more sort of, I think even more aesthetic, is E to the power of I pi, so e raised to I times pi is -1. It's just a special case. If you substitute x equals pi, this just falls out of the general Euler equation. And the reason this is super interesting is because it has, perhaps the three most famous numbers all coming together. E, like the most famous irrational number is probably, is probably pi, followed by e, and then this I, which is the square root of -1, and they all come together and they equal -1. I mean, I think that's beautiful. If I had to pick a bigger set, I think Maxwell's equations of
Maxwell's, that's a good
are
one.
beautiful too. And they're again they're a little more complicated to state. Maybe more. I guess maybe Euler's also is specialized, but
Yeah. Well, and technically, the question is, what is your favorite equation? So you get one.
right.
So Maxwell is what, 3?
Yeah.
So that's a
I'm sure you
loophole.
could, if you allow vectors.
So the
maybe
other
you can-
popular answer is Gibbs free energy equation,
Yeah.
which makes sense. It's the other universal elegant, describes pretty much everything.
Yeah. If you get out of math, and I don't know, are there equations out of physics, away from physics, chemistry, and math? Right, like what's the most famous equation in biology? I don't know.
I'm sure there's
I'm not asking my a favorite, but
I mean, but Gibbs would fall under that for some
Right,
things,
okay, the
like
thermodynamics,
entropy is
right.
another. I'm sure there's population dynamics and all sorts of stuff. So
right, sure, yeah.
yeah.
Maybe predator prey.
All right, so the prediction is done. What is the outcome? Did Charles Goodyear start the namesake company? Did he start the Goodyear company?
So he did. I'm being predictable. So the answer is no, he didn't.
False. The answer is false.
False is the correct answer, right? So Charles Goodyear, the thing that he did do was he found that Charles Goodyear was actually was rich most of his life. He was an American. He was a sort of a classic entrepreneur. I mean, he did lots of things, made tons of money.
All right, I'm going to change. We're going to go to next game, but
Okay.
keep talking.
And then he found a way. So the problem he worked on, which sort of relates to rubber, was natural rubber at that time was would rot. It was pretty low quality and it would rot. And so what Charles Goodyear did find was that if you sort of heated it with sulfur, then sulfur would form these covalent bonds, and then it would make vulcanized rubber, right, which was much stronger, much more durable. Unfortunately, he couldn't enforce the patent on this, and he actually went bankrupt, actually more than once, while he was doing all of this. And so he actually didn't make a penny out of vulcanized.
Really, I didn't know that. So he came up with the process and didn't make money off
because
of it.
there were other people who were working with again maybe Stigler's law of economy or something, there were his patent was contested. He never could sort of make money off of that. But he actually was fairly stoic about it, right? So he actually said, I mean he died without having made money off of that. So there was this other guy called Sieberling, who started this Goodyear rubber and tire company in Akron, Ohio, in 1898 as a tribute to Goodyear. So it's sort of like Elon Musk starting Tesla as a tribute to
Nikola Tesla, yeah.
Right? So it's sort
Who
of
also died poor.
was that?
Who also died without.
That's right. Maybe the palace.
What are you drinking? That is the easiest question of the night. We were drinking High Ally, the Cigar City beer from Tampa. Sorry, there's a green screen that's kind of screwing it up because the cup is green. But we have Nightbot to take care of the rest. So there's a link to the beer we're drinking. It's a High Ally Indian Pale Ale from Cigar City, which is located in Tampa. Happy Polymer wants to know, what is your favorite polymer?
So you're not gonna like this answer. My favorite polymer as a modeler is polyethylene.
Polyethylene.
And the reason is because it's simple. Like, it's no complications, right? So it's just say it's C and H4.
Yep.
So it's the easiest. I mean, I say easiest, but it's not that easy. So polyethylene, but if I had to pick a, yeah, I mean, like DNA is a kind of it's definitely a polymer. It's not a plastic, but it's a polymer. I mean, that's definitely more interesting. But it's
So your favorite as a modeler is polyethylene.
yeah, just because of its simplicity.
it's one of the easier polymers.
Yeah, you don't have to
model.
worry about. You can. And polyethylene also is one of the, you can recycle polyethylene. So, I mean, in principle at least. So, in principle.
Texas Space Agency that's fair. It's kind of a boring answer.
Yeah. The boring hides it, right? Because maybe so the interesting parts of polymers are maybe somewhere else too, right? So for example, I mean, polyethylene is boring, but between polyethylene and polypropylene, that accounts for like well over half of the polymer produced of plastics produced in the world today.
Yeah, synthetic.
Just by volume, okay, probably not by dollar amount, but synthetic plastics.
Oh no.
Ken, I'm sorry, you have to sort of.
No worries. So I take my Mario gameplay very seriously.
Oh right, okay.
Yeah. No, I speed run like 2 or 3.
Oh, I actually haven't done that.
So like this, so there's I don't know if you've heard of speed running, but it's trying to beat games as fast as you can.
Oh.
And this is one of the most optimized games in
for
speed running. Yeah. And so they're within basically 2 frames of computer simulated speed. So they execute for 5 minutes perfectly to beat this game.
I almost want to see you play this.
No, it's all your
Out of protocol.
we can after stream, but yeah, the current record is it's like 5 minutes 54 seconds 0.7
To finish
something.
the first stream?
No, to finish the entire game.
The entire game?
Yes, they beat 8 levels with warps in.
That can't be true. Like
No, it's
5
100%
seconds?
true. 5 minutes.
5 minutes. Okay.
We need some glass fiber reinforcements. We all need glass fiber reinforcements. All right. All right. Going to my list of questions, I have a few for you. Actually, we should do another. Let's squeeze in another prediction. Which one of these do you want to do?
You can pick whichever. Yeah, maybe that. Maybe number 2. Maybe.
Number 2. All right, we got a polymer question. Following up on favorite polymer. Nylon is obviously a popular answer. Keep in mind, everyone in the audience, you are on the Ask a Scientist Gaming honor code. You can't Google these answers. Instead, you have to rely on intuition or expertise that you have already. And gamble your internet points accordingly. The question is, nylon, what was that created in the 40s or 50s?
No, 1930s.
1930s, okay.
Yeah.
30 nylon was created. Does it get its name from a combination of NY, which is New York, and London? So nylon could be a contraction of New York and London. The question is that where it's got its name? Is it true or false that nylon is named after a combination of New York and London? That's a fun question.
Yeah.
And that's a 1930s, like, there are histories of naming collaborative things together and making contractions of names or naming it after a colleague or someone respected in the community. It's a fun question. Does nylon get its name from New York and London? 1930s.
Yep.
That's...
So there's actually, yeah, I mean, I have that as a factor, but this was, like in science, right? So sometimes theory is years ahead of practice, and sometimes it's the other way around. This is completely a case of the other way around, where practice, where practice was far ahead of theory. I mean, at this point, people didn't even know whether macromolecules were a thing. The nature of polymers was unclear. That didn't stop people from tinkering around and
Exactly.
I mean, that's always
if you make a material and it's useful, like
Right.
you use it, right? CFCs, leaded gasoline.
right.
Before you know the composition and yeah, go all
Well,
in.
you picked two. I was trying to spin this in a positive way, but you picked the two.
Yeah, the two most negative
Two
examples.
negative examples. Yeah.
But interesting nonetheless.
Yep.
All right, time's running out. Does nylon get its name from New York and London, a contraction of the two names? And the answer is... Sachin, what's the answer?
The answer is false.
Did not. It is
Did
just a
not.
coincidence. It's called nylon and could be a contraction of New York and London, but it is not.
And this is actually a very popular urban legend, right? Which I believed too, until somebody asked me as a question.
Yeah.
And I don't remember where I first heard it, but I was fairly confident that the other person was wrong. And then the actual story is, I mean, I should have known this, right? Because I know nylon was discovered in, there was nothing British about this. This was an American story, right? This was invented, in DuPont by this guy Carruthers, and company. There's no London connection for, why London, right? So it was discovered in Delaware, right? And the actual, I think the real story is not that, so one of the first sort of big uses of nylon was stockings, right? And stockings used to run. And so nylon was like this thing, was a material, which, so initially I think they wanted to call it something like no run. And then that was not factually true because, you could still get runs if you made nylon stockings. And then they called it then they want to call it neuron or something. That sounded too biological. And then, they said a lot. So the actual story is fairly pedestrian. Not as interesting. Doesn't connect things.
It was invented by Sir Frederick Nylon III, nephew of Duke of Spandex. Thank you, Texas Space Agency.
Right.
I mean, this...
Stigler's Law.
Yeah, exactly. Stigler's Law, which Goodyear actually, that applied.
Right, yeah.
Nylon.
It did, right?
That's pretty amazing. I like it. All right, I'm going to throw some of my standard questions in there. So I've seen a lot of movies. I like movies a lot. We've been a cord cutter family for like 15 years. What movie or TV show gets your discipline wrong? What gets it right? Discipline broadly defined.
Yeah. Right, so, I guess one could answer that. Right, so one is, if I think of my discipline as being computers, then, so anything related with cracking guessing passwords or hacking, right? I think that it makes it like in a few minutes, like you want to find a killer, you guess at passwords or hack systems. I feel like that's done and under pressure, right? Debugging a code is you can be bad as is, right?
Yeah.
In the best of.
It just doesn't look good on camera.
Yeah,
No, Texas Space Agency. Have you seen Swordfish, the John Travolta movie?
I have, but I don't remember. Is
it John Travolta? It's got Wolverine in it. Hugh Jackman as well. Yes. No.
What's the scene? What's the scene?
Hacking doesn't typically have 3D graphics. There's a 90s movie called Hackers, which is pretty spectacular. It's Angelina Jolie and a few other people. What's his name? He played Shaggy is in it as well. There's some really classic hacking movies, but have you seen Social Network?
Yeah, I did. Yeah.
So that was probably the most honest portrayal.
Yeah.
If you remember that scene where he was like trying to like script taking images from a archive and putting it in.
Yeah.
Like it seemed like an honest portrayal.
Yeah,
I'm not
yeah.
a programmer, but
Yeah.
the worst hacking scene comes from an episode of CSI. So I showed Sachin this list of questions and then I immediately showed him that scene because that is the perfect example of just the worst possible fuck up in terms of conveying programming in a just terrible way. If you guys haven't seen it, you should watch it. It is absolutely amazing. Just look up CSI hacking something. It's two people typing on one computer. Oh man, speaking of scientific like inaccurate movies, anytime anyone asks me in this future, my new answer to this question will always be Tomorrow War. Have you seen this on Amazon Prime? It stars Chris Pratt. It's like super advertised and hyped up movie on Amazon Prime. Big budget July release. Yeah. It gets every single aspect of science wrong. From physics to chemistry to biology. I ranted about this went to lunch with a colleague and just ranted about this movie for like 2 hours. It was amazing.
I should watch it just for that. Right?
Oh no, you definitely should because you're like, not only does it get the science wrong, but it like gets just basic human
play a game on how
making.
many how many mistakes can you find, right? Like how many
Man, it's something else. Like just bad decision making and I just so it goes. But yeah, programming is probably the hardest thing to depict in an interesting way on camera.
That's right.
Which is why they fake it, right? It's just not Anyone that programs, I think that is the default answer. That might be, I think that was Eugene Duprin's answer as well, actually. All right, so anyone just joining us, this is Ask a Scientist Gaming. We play video games and talk science. Mediocre gameplay combined with expert level science. Sachin
I'm taking that to a new level, right? New level of mediocrity.
It's fine. You have infinite lives. No one cares. And it's Mario. It's a classic. But yeah, we have Sachin Shanbhag, who's answering questions about soft materials, modeling soft materials, Monte Carlo simulations as applied to various different things. Feel free to throw your questions in chat. We'll also talk about computer languages, computer programming, machine learning, artificial intelligence. It is all fair game tonight. We're sufficiently drunk and in gaming that we are happy to talk about anything. So throw any comments, questions you have in chat, and we will try to address them, including CSI hacking scenes. It's amazing. 2 people on one keyboard hacking. Fighting the virus in real time. That's an amazing scene. Yeah. Oh man. I like it. I'm glad it exists. So how long has it been since you played Mario?
What's your guess?
I mean, the game is 35 years old.
Right, so that may be fairly close. I'm 44, so between
3 decades or so. Yeah. I mean, it's a classic. A lot of our guests want to play Mario.
Yeah,
this is for those of you that don't know, if you bought a Nintendo back in the day, this was the game that came with the Nintendo. Yep. And so if you accumulate like a combination of the Famicom system, which is Japan, which 1 in 4 families in Japan owned, plus the Nintendo system, plus every re-release of this game, it's something like 1 billion copies of this have been sold and played by people. So this is like one of the most iconic games. In fact, I think there was a survey at one point that Mario was the most recognizable person or character on planet Earth.
Is that right? More
so than Mickey Mouse or Michael Jordan or any of those things. So
wow.
Yeah. So yeah.
Like, isn't Nintendo's like video game story kind of like it's I think I forget the history, but like
it started out as a card game company. And
so like a 100-year-old company.
Yeah, it's more than 100 at this point. Yeah. It's something like 130. In fact, I could.
Yeah, I wouldn't be surprised. Yeah, it was like a Mattel or a Hasbro.
Yeah, so they started in 1889 as a card trading and game playing company, and then they dove into the video game industry.
So like I almost feel like there's this one. Okay, maybe I'm misremembering, but there was this one guy.
Miyamoto, yes. He came up with Mario, Kirby, like all the iconic major players in the Mario archive or the Nintendo archive. Yeah, he was the go-to guy.
And like, And I feel like like for the longest time, he wasn't even like, like his genius was unappreciated for the longest time, wasn't it? Like he was
I mean,
not a particularly great student. And maybe he didn't even start as maybe at Nintendo. He started like, wasn't his job something else? Like
I don't know his backstory.
I think his backstory is fascinating. I don't know the backstory. I just know that it is interesting.
Exactly.
I think I've heard it once before.
Ooh, Texas Space Agency does ask the question, do you know how many times I blew into my Mario cartridge? I don't know that answer, but the real answer is that doesn't actually
help.
It didn't do anything. It was all placebo effect, but so it goes. Chances are your contacts were just like loose and bending up and it wasn't making good contact, but so
Isn't
it
that
goes.
like pressing the up button on an elevator? Right?
Yeah, exactly.
It doesn't really help, but
I mean, and
helps.
half the road crossing like buttons don't actually do anything. When you do that,
Right?
yeah, they're all placebo effect. Very
you know that
rarely,
for a fact?
yeah, they're programmed to time based on traffic and not people. Because
why
people
put that in? Oh, it's just placebo.
Yeah, no, it feels like you're doing something
Wow.
while you're standing there.
So that
it makes
people
you
won't
feel
just
better.
walk in, huh?
Yeah,
Like won't jaywalk.
Yeah.
Wow. Like knowing this, has this changed your behavior?
Not really, because just for safety reasons. I'm not going to risk going early, but big spooky skeleton. Super Mario 3 was the top-selling video game ever for a really long time before Minecraft blew it out of the water. Are you familiar with Minecraft?
I mean, I know it as a name.
Yeah.
As you can tell,
But yeah, Minecraft is, I mean, it's unlimited like building space, right? You get different materials to build things, and people have made like entire worlds. They've made computers, they've made calculators. Like you can generate anything that requires bits of spatial programming.
Right. Yeah. Did you ever play Sims?
I did play Sims.
I did. I just knew people who did.
I played Sim Ant, which was where you got to play as an ant against other ants. It was ant warfare. That was one of my classic favorite games. Sim Ant. So I have a cheat code for this where I can, if you get a mushroom, you can stay big until you fall in a hole. You want to do that?
Yeah, I mean, you can do that, but as you'll find out, it won't help me much. I'll fall in the first ditch.
It's fine. We'll take it as is. All right. There we go.
Oops. Okay. Yeah, I'm gonna use the super fast button. I realize I can use that now.
All right. Question from Texas Space Agency: is there plastic I can use on my greenhouse that meets all the requirements for greenhouse roof, but will be hail-proof? So greenhouse, presumably you want a lot of photons to get through.
So something transparent.
Yep.
Right?
But hail-proof.
Yeah, I don't know the answer, but something like PMMA, right? That's very transparent, right? I mean, you can use that.
Yeah, it's pressed correctly.
Eyewear,
Yeah,
right? It's like that would satisfy that requirement. And I'm sure you could make it. Like you could blend it with some other materials to make it hard enough. But I don't know. I don't honestly. I don't know whether that's possible. It seems like a very possible. It's possible to engineer. But super transparent. I mean, you may make it super transparent, but if you live in Tallahassee,
you don't need it.
like pollen, or you may that'll probably ruin, right? I mean, I don't know. So maybe it's best not to sort of over optimize on the transparency.
That's a good point. No, so they had that issue with the solar farms actually early on. As it was any amount of dust or pollen or anything that lands on the solar cell, you reduce your efficiency by a lot,
right?
Because it's scattering, right? And they found it was more cost effective to pay someone to walk around and wash them off constantly.
Is that right?
Yeah, because it's the amount of energy lost on if you have a square kilometer of solar cells. That's a non-trivial loss.
Yeah. So I just got solar panels installed.
Oh, you did? That's awesome.
Like it's not even been turned on. Like it's not hooked to the utility.
Yeah. So it's on your roof. You have the panels,
and it's all set up, right?
Huh.
And like I was told, I have to clean them up. I have to clean them every year.
Yeah, or more.
Right? Like he said once a year. I don't know. The good thing is you can monitor
Mm-hmm.
their efficiency going up or down.
Just another question. But yeah, that's awesome that you have solar panels and you have enough light, incident light,
So
that's
we,
going to be
I
useful.
mean, I should have done this a long time ago.
Yeah.
It's just that when I first investigated, it seemed like, it doesn't make as much sense. I mean, just monetary sense.
I mean, 10 years ago, that might have
That's
been
right,
true.
10 years ago. And then I didn't look. And now, actually, I mean, if you have a roof that faces the right way, and if you don't have trees in that direction, it's actually very, I mean, like you can make a purely economic case.
Yeah.
Like you don't even have to make a.
Well, there's websites that'll look at your like Google Maps, like tree population, and say,
Right.
will this get enough sunlight in this
So
region to
there's-
be cost
In fact,
effective?
there's like this Google, like there's actually a Google own. So to get past this, I have to jump there and then jump across. Okay.
Yep.
Okay. I think like Google Solar Roof or something. I mean, they'll tell you how much
Yep. If it's
you know,
cost effective. Yep.
and how many panels you will need and stuff like that.
No, that's awesome that you have that. Like we looked into it, but we have way too many trees.
It's
It's
too many
not.
trees,
It
yeah.
blocks too
Like,
much
yeah.
light. But I mean,
So we have the perfect roof. We have like a south-facing roof.
Yep.
It's a large enough space so that it's not even very unaesthetic. I mean, it's just a big rectangle. I don't need them in. They're not in a sort of a weird configuration.
Uh-huh. What company did you go through?
So we got quotes from 3 local companies. Eventually we went through IGT Solar. But they all, I mean, they like all of them seem like they if you have a preference for a certain type of panels, they will install.
That's awesome. I mean, it's cost effective. So if you don't mind me asking, you did everything up front cost on it, or you're paying it through a loan program?
No, I'm doing everything up front. I mean, you can get loans if you wanted to.
Yeah.
But so our power consumption is not like I mean, so I checked. So I know I didn't know this before, but I know this now, right? So our average daily power consumption is between 25 and 30 sort of kilowatt hours a day. And so so right now we just have 15 of these panels. The nice thing about the solar panels now is they're very modular, right? So you can, like, tomorrow, let's say you buy a Tesla or you have your electricity needs increase, you can just, like Lego, you can add a few more of the panels.
So 15 panels, is that matches your needs?
So,
what does that do?
Right, so you want to go slightly under, just
Okay.
because of the way the city. I mean, that's just a local decision, right? So the city does this net metering, right? So you get every kilowatt hour you generate. So it's kind of interesting. I mean, I learned a few things while I was doing this. Maybe you're a chemist, you probably know all of this. And so I would have thought that the best months for electricity would be the summer, right? I mean, the sun's out for so long. Turns out that's not true.
Air conditioning.
That's one, and the other is like the materials that make up these panels work best at lower temperatures. Their highest efficiency is at lower temperatures.
That's interesting. Yeah.
And so July and August tend to be either like break-even months or months that you actually draw from the utility. So February, March, and just Tallahassee, right? Because our that time of the year is not that cold, and then even though the day is shorter, the fact that it is cooler makes it sort of your your net meter, like your credit sort of is going up during those months.
No, that makes sense. I mean, it's something I've thought a lot about, but I know how solar cells work, but I don't know the economic end of things.
Right.
And that's something that's really stupid in Florida. So in California, they basically implemented a system where you could work with a company where you had said, will pay under my normal electric bill for the next 15 years, and they would install solar panels on your house, right? So you're basically committing to a electric bill but you'll have solar panels. They made that illegal in Florida.
Is that right?
Yeah, and so it was lobbied heavily by the local electric or whatever companies, and basically they made that illegal.
So what exactly is illegal?
It's this idea of like leasing the solar cells kind of thing.
You can't. Is that right?
Yeah, and it's very particular in that they can't like charge you monthly for it over a certain time interval. So they did really weird rules about it. That it's in California.
But so, like a couple of interesting rules even in Florida. So thing I didn't know, like I the first thing I did when this idea came up was, you got to check with the HOA, right?
Yeah.
HOA.
If it's okay.
And I don't live in Southwood, but but apparently no HOA, like an HOA in the state of Florida cannot object to you putting solar panels.
Really?
So there's actually protections.
There are a few from homeowners associations.
Yeah.
That's probably worthwhile. Anyone that hasn't bought a house, make sure you check if there's a homeowners association before you buy a house and see how shitty they are as human beings, because it can be bad. It can be really bad. And it can cost you a lot if they're opposed to certain things you do. No, that's interesting. I didn't know that was actually protected.
Like a Florida law, which
it's pretty amazing. So you could just get the most gaudy, like pink and purple solar cells, and they can't say shit.
They can't do anything. right.
That's amazing.
Come on. Stop here.
The battle continues. I like it. All right, so anyone just joining us, again, and this is Ask a Scientist Gaming, mediocre gameplay with expert level science. Today my guest is Sachin Shanbhag, who's an expert in modeling soft materials. He's a computer scientist and an engineer. Likes to model and study the behaviors of soft materials, including things from like proteins, DNA, maybe cellulose, synthetic polymers, whatever it is, they kind of obey the same modeling type behaviors. And so that's the kind of stuff that he's interested in. So if you have questions, throw them in chat. We're happy to answer those. If not, we're happy to keep talking. We go where the road takes us. Speaking of which, soft materials, non-Newtonian soft materials. Is that intrinsically interesting from a computational perspective?
Yeah.
Well, first, what are non-Newtonian materials?
Right.
And are they interesting?
Right. So, I almost feel like I should tell a small anecdote. Right?
No, do it.
So my advisor, right? Like periodically libraries get into trouble, and then they look at what journals they subscribe to, and then they figure out what to cull and what to keep, right?
Yep.
And so he used to work at so my advisor, before he became a professor at Bell Labs at Michigan. He used to work at Bell Labs, and they used to subscribe to this journal called Journal of Non-Newtonian Mechanics. And whoever was the head of the library wanted to sort of get rid of that journal, because he said, nobody here works on like relativistic physics, right? Because like non-Newtonian, that person felt like relativistic, right? But here what Newtonian refers to is right. So fluids can be Newtonian or non-Newtonian. So examples of Newtonian fluids are things like water and air. And what characterizes a Newtonian fluid? So things that have a unique viscosity are Newtonian fluids. So if you think about shearing materials, right? A Newtonian fluid has the same viscosity regardless of how fast or slow you shear it.
Do you want me to get you through this level?
Yeah, maybe.
All right.
Make it seem so easy.
Most of these, you just got to go fast.
Whoa!
Oh, Bowser. I got physics fucked on that platform. But believe it or not, most Mario levels, if you go fast, they're actually easier than if you go slow. Yeah, because look at these fireballs.
You can jump farther.
I'm not doing anything. Then I'll jump over that.
Oh, you could just... Oh,
yeah. So the timing works out really nice. I don't know if they intentionally did this or it's accidental. But yeah, sometimes it's easier to go fast.
I'll try that.
All right.
Yeah, so Newtonian fluids are that, right? The viscosity is independent of how fast or slow you shear. But there are other materials where the viscosity of you feel depends on the shear rate. And a classic example is, maybe, for those of you who live in Florida or close to a beach, if you've ever sort of stuck your feet inside wet sand, like all the way in.
Oh, that's interesting.
Like when you try to move your feet, maybe you've sort of noticed that the faster you try to move it, the harder it gets to move them. And so this is an example of it's a class. So wet sand, for example, would be a non-Newtonian fluid. It's a particular kind of non-Newtonian fluid. It would be called it's shear hardening. So its viscosity goes up as you shear it. Like you try to shear it more, it feels like it's more viscous. That's not the behavior of all materials. Like lots of there's plenty of stuff. Right?
Doesn't matter. We got a cheat code.
Oh, you did? You already did that?
No, I give you the cheat code. You're stay big.
So there are other materials which are shear thinning. So the faster you shear them, the lower their viscosity. And so materials which do that, whose viscosity changes, when you shear them fast or shear or deform them fast or slow, those are called non-Newtonian fluids, right? So their viscosity is not constant.
The sand on the beach is a really fun example. Like there's also like a chemistry like kids exercise where you make like I don't remember what it is. It's like starch or saccharin or something like that. You can actually generate this. It's super glue type material where if you punch it hardens and stuff.
So like even something like what the kids like what's that like silly putty, but just what's that thing called? Like kids make it a lot. Your kids will make it too. It's like annoying because it sticks everywhere.
You'll find it everywhere.
Like you and you put in an adhesive and borax.
Yeah.
The word's not coming to me.
I know what you're talking about. Yeah.
It's like
ooh, a vine. Nice. What's up? So they are unique and they have very different behaviors.
Yeah.
And modeling, you guys still account for that.
Yeah. Should I have known that?
The music intensity is really ramped up. When you get under the 1 minute mark, that's when it gets serious in Mario. Happy Polymer has a question. What kind of modeling are you interested in now? Is there anything new?
I touched on this a little bit before. But one thing that one thing I've been experimenting with, especially a lot like the last year, is to try and use some machine learning. I've always wanted to try and see how I could sort of incorporate some machine learning in my and I was like, one thing that always bothered me was, one of the problems was what I just what I said before, which is the machine's learned, but do I understand what the machine has learned? And the other problem was the other problem was you learn a model, you learned a machine learned model, but how self-aware is that model? Like, does the model know like whether it's right or wrong, right? So maybe like just to pick an example that this is not a materials example, but if you're training a neural net to learn to detect sunsets, and maybe you give it like maybe a picture of a duck, right? Can it will it be able, right? So okay, maybe that was a bad example. So right, so like there are times when I want the model to do a prediction, but if it is truly unable to do that prediction, it should tell me that it can do the prediction. So I want some sort of like uncertainty quantification. Along with the prediction it gives me, right? And and it turns out there are machine learning techniques which let you do that, right? It was just that, it would have been easier for me to say, oh, like I don't, like there is nothing there, and oops, and sort of, oops, okay, I shouldn't worry, right?
No, just keep going. Just don't fall
Just
in
don't
a hole.
fall in a ditch.
Yeah,
right?
that's it.
Which I will promptly do, right? I'm pretty
We will highlight that clip. It'll be on YouTube forever. Here it is.
Barely, huh? The art of barely.
So machine learning, it's so hot right now.
Yeah.
It's such a big area. I'm glad like scientific computing department seems positioned so perfectly for machine learning and AI. Like
Yeah.
I think I'm advocating for this in my department as well as like at a university level. We need a hiring initiative in that area.
Yeah, so there's
Like-
a new, I don't know if you've heard of this, but there's a new data science master's
Yeah.
at the university, which is like a cross between 4 departments. I mean, yeah.
That's awesome.
But I like the fun's always in the interfaces, right? You
Yeah.
like traditional areas get farmed out fairly quickly,
Yep.
and then the
Find the
interesting
money
questions
between.
are always at the. Oops. Okay, gotta do that first. Oops.
Have you watched machine learning algorithms play video games like this?
Yeah.
So there's a really awesome example of this. Is one classic game where so you have to, if you're going to do machine learning, you have to give it some kind of goal, right? You have to give it like maybe it's the number of points that's generated. One particular parameter somebody input on a machine learning video game exercise was new information. So if it didn't see the same screen again, it mean you had to increase to an additional level. But what the machine learning actually ended up doing, instead of completing new levels, it found a way to glitch the screen so it was just white noise. So it would clip into the wall until it made like static, and all that static was new information continuously. And so based on that parameter, it was winning the game by making static
what you
noise.
ask for.
Yeah, exactly. No, it's a very monkey's paw scenario, right? Where you ask for it and it gives you what you want, but it doesn't fulfill the goals of what you actually wanted to do.
Yeah.
So,
I mean, have you heard of like all of this? I mean, a lot of machine learning models. I mean, not the ones for materials, but like they're trained on existing data. Right?
yeah.
Have you? I don't know. Like people seem to sort of worry about whether their learning are biases.
Yeah.
Like there's an entire ethics of
No,
I mean, it completely.
I had a major discussion about this with when we used to do in-person Ask a Scientist. George Pesto, he's in criminology at FSU.
Okay.
And so they're trying to do like machine learning in terms of prison sentences and recidivism rate, but there's an intrinsic bias in prison sentences against minorities. And so your data set is already biased against the outcome.
right. Yeah.
And so that's a high impact scenario where it's biased.
Like even like hiring, right? I mean,
yeah, exactly.
if people who went to like really good, like good places, good universities got hired, did seem to do well, let's say at a company like Google,
Yep.
maybe that makes them
yeah.
pick even more of the same people, right? Regardless, because that fits.
Yeah, no, it self-propagates.
So it's like our human biases. Maybe maybe you're making them too human.
So like, are you familiar with the Sloan Award for like chemistry and chemical engineering?
Yeah.
So after I didn't get that award after applying, I went through and I looked at who got it. And I basically saw it was dictated by you needed to do a postdoc at MIT, Berkeley, or Caltech. And so it had nothing to do with the number of publications, nothing to do with the number of citations. It was biased towards that person data set. And then if you do machine learning, obviously that entire thing is biased towards those individuals.
It just perpetrates.
Yeah, exactly.
Perpetuates. Right?
Yeah. And it's like humans were not great at this, but machines aren't any better because that's it's
like
garbage in, garbage
you're
out.
right. You're when you said that when you remarked that AI playing that game optimized for like sometimes what you ask for.
Yeah. It's not what you want.
It's not what you intend.
yeah. So that's the what we describe as the monkey paw scenario. Are you familiar with monkey paw?
What is that? Oops.
It's this. I don't know where it came from, but the first time I saw it was actually on The Simpsons. But like, if you have a monkey paw that gives you 3 wishes with 3 fingers and it lets you decide, and your wish is, I want my grandma back and she died 20 years ago.
Okay.
They might bring back a cadaver that's a zombie.
Yeah.
Right? So if you're not very explicit in defining your parameters,
Yeah.
your answer will come back garbage.
Yeah.
Right? So that monkey paw scenario, if you're not very explicit in how you're defining your success and stuff, you get monkey pawed, basically. So I think it's a very poignant descriptor of that phenomena, right? And machine learning is suffering from it. AI is suffering from it because you have to give it those rules, but you don't want to be too strict because you want it to be slightly creative.
Right.
So
like AI is playing games. I mean, I'm sure, since you're so hooked into games, you probably know that. So like, have you seen that the place where the AI learned to play Pong?
Yes.
And then it learns these different things that humans don't use much, right?
Or can't even execute, right? Yeah. No, it's very, very true. That's why I love that space. Like they can explore things we don't.
Right. And like, like even though I say machine learning can't find, like I may not understand machine learning models. I mean, they're pretty good at sort of finding these non-linear patterns in data that I might never be able to find. So instead of being sort of pissed off that I can't understand the answer, maybe I should just be happy that it's, it
exists. Yeah.
It exists. Right?
No, it's true. I mean, it's one of those things, but how much in our life is driven by just sheer empirical data? We don't know foundationally why it happened. And the answer is a lot, right?
That's right, yeah.
Like, I mean, how long food spoils, that's an empirical model. It is not ab initio. It's not from fundamental principles. Right. So if we're okay with it there, maybe we should be okay with it more places. It's discomforting.
Actually, you pick up an interesting example, like just the amount of, I feel like the kitchen or like in general is a great laboratory for all kinds of science, right?
Yeah.
You could do physics, you could do chemistry, you could do biology, you're fermenting stuff. But and maybe now you should do AI kind of stuff. You should make up recipes, right? Like you say, okay, these are recipes that exist across the world. Make me a new, I have this in my refrigerator.
Yeah.
Just like.
I mean, what's amazing is you could automate that. You could have a robot do that, like cooking. Absolutely. I would watch the shit out of that cooking show. Have AI just generate food from a sampling of things, and then have like 3 Michelin star judges just like, is this good or bad? Somebody write this down and sell this to, I don't know, what Discovery Channel or Lifetime? Or, I don't know who would do that. No longer the Learning Channel. They're all reality TV, so maybe that's an option. Yeah. All right, back to things. Texas Space Agency, how would you respond to the statement, one thing is true of all models, they are all wrong, the rest is just sigma x. So that's presumably sigma as standard deviation from median. I don't know sigma x, but you don't have a clue how long it took me to get a sigma in Twitch chat. That is amazing. Did you copy and paste it into Twitch? But yeah, models are good until they're not good. That's a fair critique.
Yeah. So I think that's spot on, right? Like models are maps.
Yeah.
And the map is not the place, right? So I mean, there's this famous saying, right? The best model of a cat is another cat. The best model of a cat is a cat, preferably the same one, right? I mean, but models are still useful, right?
Yeah.
So if you want to have the classic example is like actual maps, right? I mean, you could do like a map, like a maybe a satellite view on Google Maps. But maybe that is too much detail. Maybe you don't want to see, where the trees are, or maybe just a regular sort of non-cartographic map is helpful. Or maybe you're using public transport and you just want to move from one place to the other, and you're taking the metro. In which case, the relevant map is not even, like how far away one place is from the other, but really how long it takes for the train to go from one stop to the other, right? I completely agree. All models are wrong. The question is, are they helpful? The last part of the question I don't understand. The rest is noise. Is that what it is?
I don't know what sigma x is.
I feel like you spend a lot of time. If you spend a lot of time writing that sigma. Maybe you should tell us what you mean by that sigma.
Yeah, let's
maybe
earn
it'll
it.
take less time.
All right, Reese's Pieces redeemed. Take a drink. So,
Oh, okay,
Sachin,
yeah.
cheers. Thank you again for swinging by. Ask a Scientist Gaming, mediocre gameplay, expert level science. All right. I mean, that's the thing about models. They're accurate within a certain parameter space, and is that parameter space good enough? Most of the time, yes, right?
Yeah.
It's just,
I mean, usefulness, sometimes, like accuracy is not all that it's cracked up to be, right?
Yeah.
So we write some models for predictions. Some models we write just for, just to sharpen our questions or to improve our understanding, to figure out which parameters are the important parameters. In fact, the more accurate a model is, often the more complicated it is, right? And the more complicated a certain model is, the harder it is to sort of, I don't know, like grok it, to like truly understand.
yeah. Well, not just
the different
understand,
features.
but also apply and like use.
Right,
And
absolutely,
yeah,
right.
utility goes down the more complex it becomes.
Almost always, right?
Yeah. Yeah.
And so there's this, like, I mean, I have a particularly soft corner for inaccurate, not necessarily accurate, but simple models, right? So, I mean, that's what, everybody has a preference. My preference sort of is strongly in that direction because, I don't know. I feel like simple models can teach us a lot, right?
All right. Sorry to interrupt. It's 10:15.
Okay.
Is it time for the next game?
We should.
Ladies and gentlemen, yes, take a break.
Okay.
Use the bathroom. We'll hang out in the meantime. Cheers again to anyone just joining us. I'm Ken Hansen, Associate Professor in Chemistry and Biochemistry. I do solar cell light matter interactions. Joining me today is Sachin Shanbhag, who studies soft materials, modeling materials, computational modeling, big data sets, processing that, and also most recently machine learning and its applications. So if you have any questions, feel free to throw them in chat. He's also programmed in things like Fortran. I think he talked about C++ as well as Python, and most recently Julia, which is a new computer science programming software package. So yeah, if you have any questions about any of those things, feel free to throw them in chat. We have been playing Mario. I think it's time to move on to NARC. It's the all-time classic. I'll wait for Sachin to come back to introduce this game. But yeah, this is our... we play this pretty much every time we do Ask a Scientist Gaming, and this is basically enforced by me. Fortran. Did he also use punch cards? Harsh. How dare you say that about Fortran? All right, copying and pasting a few questions to make sure we get them. Fortran. So one of the comments here, Fortran, did you also use punch cards? Harsh. Harsh.
I missed that by a decade. I think.
At least a decade. When did they stop using punch cards? That would have been 1960s.
Probably
Common use.
So Fortran was a big deal, right? Because really, today Fortran seems like a cumbersome language to use, but sorry.
All right, ladies and gentlemen, we are on to NARC. We're going to win the war on drugs once again for Ask a Scientist Gaming. So for those of you not familiar, we play this at the close of every single Ask a Scientist Gaming, at least so far. This is a terrible game that started the video games cause violence epidemic, but the goal is to stop the drug dealers and win the war on drugs. So yeah, Sachin is playing NARC for the first time, and he has kindly volunteered to take on this challenge. So yes, we are going to beat Mr. Big tonight. We have approximately 42 minutes to make this happen.
Oh, is that right? Okay.
No hurry though, no pressure. You got to win the war on drugs in 42 minutes. All right, Fortran. Sorry, it was the breakthrough language. It was important.
I mean, at its time, it was very fancy. 40 or 50 years ago.
Just keep walking right and hold A. That's it.
Okay.
This is the best way to beat this game. Yep. Just march through them and kill everyone. Just like the real war on drugs. That is pretty dark. I apologize for that.
In the consensus now that it didn't work out too well.
Fortran, what was it like taking a horse and buggy to class? The youngins are talking shit.
I know the horse and the buggy were a big improvement over whatever was before the horse and the buggy,
So
right? I mean, that's what you forget.
Grab that guy right
Okay.
there. The card, the safe path.
Oh.
The red thing right there. Walk over it again. I don't know why that didn't work. Hold up. Nice. The best part, I'm only 34. So they are not that detective. But at 34, you could probably name all the Pokemon, at least the original generation of Pokemon, which I could not do at 39 years old. Like, there's a generational gap. Like, I get it. But 4chan. So are you familiar with the ab initio calculi, like Gaussian and Titan games? Games is still done in Fortran.
Yeah, I mean, lots of
it's
weather
still a
prediction.
common.
So I have a feeling a lot of actual computation people are exposed to is actually Fortran. So a lot of hurricane modeling, right? I don't know this for a fact, but I feel it would be fair to speculate that most of these hurricane models are written in Fortran. A lot of weather prediction models are written in Fortran. Lots of these basic linear algebra libraries, which underlie, which are used by a lot of other code, is written in Fortran. In fact, in a certain sense, I mean, maybe people have heard of. I need to get that first.
Yeah. The door. Yep.
Okay.
Nice.
So, some people have probably heard of this language called MATLAB, right? Matrix Laboratory MATLAB. So MATLAB was initially written as, I mean, I'm probably sort of trivializing a little more, but it was written as a wrapper on Fortran linear algebra libraries. I mean, that was what it was. I mean, it's a different beast. Now it's like a fully functioning thing, but you'd be surprised at how much it, there are people in my department who still think Fortran is something every computational scientist should know. I'm not sure if I share that view, but I don't know. I have a feeling Fortran has done more for scientific computing than many other languages.
I mean, so this is a problem we've run into in chemistry in terms of the user friendliness of software packages, right? Like, it was restricted 40 years ago to only those that could run the software and do the programming. And now I have Gaussian and Titan where I can click and check box and press go. And I get answers. I don't know if they're the right answers, but I get answers. So it's an intrinsic problem. But it's also a benefit, right? Because anyone can do it. So... But you got to kill one of these guys and get a blue card. So hold B to squat, and then you can shoot the dog.
Hold B. Oh, that's how I kill the dog.
Yeah, okay. You got to squat walk to kill the dog.
I'm just gonna squat every.
All right, I'm gonna run to the bathroom. Before I go, I'm gonna throw out a question. What was your I made it as a scientist?
Oh yeah. I mean, I don't know. I don't know if this is unique or not. So when I started my PhD, I was fairly gung ho about sort of I felt maybe I had the confidence of youth, but I felt I felt confident as a independent scientist when I was starting out my PhD than in the middle of it, right? Which is, it's kind of weird, but yeah. So but then I mean, I had a PhD advisor who was really smart. There's lots of good things. There's mostly good things I will say about him. But I quickly realized he was smarter than me, my PhD advisor. But that's no problem. I mean, I've sort of interacted with sort of people who are smart. I mean, that's maybe that's a normal day for me, right? I mean, I most of my colleagues are smarter than me. And the trouble is the way you compete with somebody who's smarter than you is you outwork them. Right? So the trouble was he outworked me. Like I was a grad student, but he came in to work before I did. Like he came in at 7 a.m. every day. He would leave at 7 p.m. So he would he would sort of leave after I went, and he worked all day Saturday. Like there was no way I could sort of outwork him. So he was smarter, he worked harder, and he already knew more. So there was a time during my PhD where I felt, like this is not for me. Like I have no edge. If this is the business and this is the I said
on there and tap B, you can jump in the car. Just a real quick. Even faster than that.
Oh.
There you go.
Oh.
Nice.
I race through?
Yep. But you're
I
gonna
can't shoot.
run into a
What?
bomb.
Okay.
That's the cruel part about this is you get the car
And
for a
I
moment.
could have controlled my car. Huh?
Yes.
Oh,
You can
okay.
go up and down and shoot rockets.
Okay.
Sorry to interrupt.
Right. So I mean, I this is good or bad. Okay. Doesn't matter. And so I mean, it took me almost towards the end of my PhD to sort of figure out that even though my advisor is smart and he outworks me, there's still a few things that I can like there was a niche. Like you don't have to be better than the other person. And so
Just gotta jump. Same thing. Tap and hold right.
tap and
Tap the B button, the one that makes you squat. So
no.
hold that guy. Hold right.
Oh.
What? Did that just freeze? No. You landed.
Oh.
That was amazing. Somebody please clip that. We had a teleportation moment. I thought the game froze and I was panicked because we're gonna win the war on drugs again tonight. But Sachin,
I might be the first person who does not.
well, you'll let down everyone in America if you don't win the war on drugs. Going back to a few questions about Pokemon. Yeah. All of us superior millennials whose brains expanded from memorizing the hundreds of Pokemon names. That is true.
Yeah.
So I'm the like very top end of millennials. So it's 1982, 1981 was when I was born.
Yeah.
But I don't know Pokemon, so clearly I've lost out on that war. So it goes.
I'll tell you.
Nope. There you go.
How did you check by this figure? Is that me?
This button right here. Yep.
Oh, you
it's
tap
weird.
it.
You got to
Okay,
tap it. And I don't know. I mean, they needed to make 4 controls for a game that has 2 buttons, so that's how
Yeah.
they did it. So this was actually an arcade game where it had 4 buttons, and they translated it to Nintendo, and it didn't come through as well as it should have. But for anyone in the audience that's been a consistent viewer of this, that we play NARC, I've decided to start speedrunning NARC. I'm going to try to beat this game as fast as I can.
You can speed run? Can you run faster?
Yeah, you can beat this game, and the current record is 9 minutes and 28 seconds. So there's a way to beat it. The hard part about this, and I learned this by watching, like I started doing my homework, watching other players. So hold B, squat. Yep, and you can shoot those guys.
Okay, the dogs, right?
Yep. So hold that button, shoot. Yep. And you shrink the dog and they run away. But I started looking at this. So are you familiar with the phrase RNG? I don't know if you've heard that before.
Random number generator.
Yeah, exactly. So video games have a certain aspect of RNG.
Yeah.
Where it's like you come across a boss and you can only beat it when certain events happen.
Uh-huh.
This is dominated by RNG. So there's certain events where if you kill a guy, he drops a card. If you don't kill him, so on and so forth.
Oh.
And so, but there's a squat and shoot. Yep, there you go.
It becomes small. Okay.
Yep, you shoot the dogs, and I'm sorry if you love dogs, but you gotta shoot the dogs to win. But I learned watching the speedruns of this, the difference between A 9-minute and 28 run and a 10-minute and 30-second run is entirely RNG. So, yeah, you just basically play until the luck goes in your favor. Unless you can figure out a way to manipulate it, in which case you can dominate some decisions over others. So, yeah, that's what I'm going to try to figure out over the next several weeks. All right, so tap B.
B.
It's a really light, like you don't even have to press it down.
Okay. Oh, come on. I thought I'd get in the middle of the road just so that I can see both sides.
No, it's a very specific pattern you have to memorize.
Yeah, you have to memorize, right?
And what's worse is, so go down and walk around. There's bombs over here.
Oh,
those
okay.
are RNG. So regardless of what you pick, it might end up screwing you over if there are bombs there.
I should just forget the car.
Texas.
I'm better off walking, I guess.
Texas Space Agency is tragically right. This is historically accurate. DEA and ATF have a known history of shooting dogs.
Is that right? Is this?
I mean, it's not unusual for police and law enforcement to shoot dogs if they're being attacked or being threatened or.
Yeah. We just got a dog like
Yeah.
3 or 4 months ago.
Oh, but back to the discussion about like intelligence versus hustle.
Yeah.
So I give a talk to the incoming grad students every single year that's about research productivity.
Yeah.
And there's a paper by William Shockley. I don't know if you know Shockley Quest for Limit, the transistor. Yeah.
I know.
He basically did a statistical analysis that looked at productivity in research, and he defined productivity as the number of papers, number of citations, number of patents, and he basically showed, like, statistically that it had nothing to do with intelligence.
Yeah.
And it was entirely correlated with your ability in certain tasks. And there was an exponential. It's not a normal distribution, it's a log normal distribution.
Okay.
As in the people that are really good are exponentially better than those that aren't.
Uh-huh.
And you can basically correlate that with the time spent and the amount of effort on a given task.
On a given task, yeah.
Yeah. And
Right,
so
yeah.
I give this talk to the students, and I can send you the PowerPoint if
Yeah,
you're interested.
yeah.
But it literally, like, intelligence is a normal distribution. So it cannot describe a log normal productivity curve.
Yeah.
And so it's a really interesting paper. I mean, Shockley had a lot of bananas ideas out there, but he also, transistor, Shockley Quest for Limit, just tap B. Nice. So if you stay on the bottom, you should be good. I think this is a problem with science, though. By this metric, the best scientists are the best administrators, not the best scientists. I mean, that's fair. And so it's a hard fundamental problem in terms of how do you assess if somebody's good. So B again to jump. Tap it. B. It's really touchy, and I'm sorry about. Yep, there you go. Press right and tap. Yep, floating. Nice. And
So I think the one thing that I mean, as you were saying this, I don't know where I found this from, but there's this guy Tukey, one of the inventors of the fast Fourier transform algorithm, who worked at Bell Labs. And there was a colleague of his who, they had a common boss. And I mean, this is anecdotal. This is not like a log normal distribution. This is not data. But like that colleague who he was doing this talk, and he asked his boss, "What makes this guy? Why is Tukey so effective? Like, how come he's like this 10x kind of scientist, right?" And Tukey really was that. I mean, he was not just a manager of a big group. He was himself extraordinarily productive, right? I mean, you can distinguish between a general who, effective general who just, who's commanding from someplace versus a commander who. That door. Okay. Thanks for all the cheat codes.
No, I'm going to save you a lot of time. It's not worth your effort to do this.
So the thing the boss said was really that if you work again, this is.
You are getting punched to death.
Yeah, I know. Oh, there's a door there, right?
Yeah. Oh no! You walk back in.
Oh, oh no!
Or take it amphetamines like Erdos. Yeah, that's one option.
No,
That's amazing. I mean, but the thing about that productivity talk is like there is a certain amount of attrition that you just need to do. One, yeah. After you go through the door, stop pressing up.
Yeah.
Well, one thing, Roy Periana, so he was one of my teachers at University of Southern California before he moved to Scripps Institute. He basically said, like, if you're going to give a raise to someone or you're going to give a promotion, how do you make that decision? And so you can't just base it on who gets the best results or who is making the most papers, because anyone can start a good project and take it to fruition, right? They can something that's working and make it work consistently over and over again.
I gotta go there.
But what he said is the people that you should reward are the people that change the direction of projects. So even if the project is working, if they come up with something new that goes a new direction, or if it's failing and they come up with something new, those are the people that are truly exceptional.
Yep.
And so it's by his metric, it's not based on total number of papers or patents. Right. It's based on who changed the direction. And I thought that was profound.
Yeah. And like a lot of this is hard to assess. Like, I mean, like I would hate to be an administrator in charge of all of this, because there is so much of judgment sort of,
Yeah. I mean, but you need metrics, and that's what sucks, right?
Yeah, but the trouble is, like, metrics stop becoming useful once you sort of make them too explicit, right? Like, because people will, I mean, isn't that like, I feel like that's a, oops.
It's the one level you go left.
Oh.
So twisting it, changing it up on you right here. We're going left in the drug farm.
So, what was I saying?
Yeah.
So, I mean, like, I feel like, in a lot of, right, so what do we say? Okay, so about, right, so, like, metrics, right? So, I need...
Sorry to interrupt. You got to kill that guy. And okay, he dropped the card. That is RNG. So he didn't have to drop that. It's like a 1 in 10 chance. So you got lucky.
Yeah. I feel lucky today. Just should Google search my way. That's like not really a thing anymore, right?
Yeah.
I feel like, I don't use the home screen. But like, like a lot of metrics start becoming useful once you sort of explicitly state that this is what you should, you can game. I feel metrics are most useful when, I feel somewhat strong. Like if it's a 100 meters race, right?
Yeah.
Where the person who runs 100 meters the fastest wins. That's a place where even if you could game the metric, that is what you want, right? That is exactly what you're measuring. Who runs 100 meters fast?
Yep.
The problem is in like a lot of, research included, but forget research. I mean, just think about how students are evaluated, right? High GPA is good, but
it's not a good predictor, right?
Right. It's not a good predictor of lots of things. Right? It's a good predictor of a few things, but it's not a good predictor of. I know this as a professor. I know this as a student too, right? I mean, like the student with the highest GPA in my class was not this. If you ask everybody, if you took a poll and said, who do you think is, I don't know, like pick your
most
objective.
Likely to
most likely to succeed, smartest, or like the best. Often, the person who gets the highest GPA person is the person who is most careful, right? Who makes the fewest mistakes, and that's useful, right? So that's useful if you are, you're an accountant or a surgeon. Maybe that is vital. You don't want to make mistakes. But if you're somebody who is, who's starting a business, maybe like what is more important is not your fail rate, but your, go there, okay. Like what's important is, right? So like imagination, right? Is more important.
Creativity.
Failing is okay.
Yeah.
And sort of exposing yourself to the right tail of sort of, possible outcomes. And that becomes really important. And single metrics, like single metrics like GPA don't capture all that.
Yeah.
But unfortunately,
that goes back to our monkey paw scenario, right?
Yeah.
Finding it on what your parameter space is, what is actual success, and that's, this is something I fight with. not gonna say I got kicked off of graduate recruiting or graduate admissions, but I was very cynical about things like GRE and GPA in terms of predicting, and research has shown this over and over again.
So in what direction?
GRE has zero correlation with your success in grad school. Like there's zero evidence to say GRE predicts anything, but somehow we still use it as a metric for admittance on a university level. It's if you try to admit somebody below a certain GRE score, you have to write
you have to write a justification, right?
Yeah, and it's not based on anything.
Why do you
real.
think that is? Like, how do you think that? Like, clearly, it wasn't always the case, right?
I don't know. Just like you want these metrics because it's easy to put somebody in a pile based on a number, but like it's
convenient. Right?
Yeah, exactly. But it doesn't actually predict anything, and so it was very frustrating. I'm like, we should roll the dice on students because we'll have more success than doing it based on GRE. And it's a battle I've fought for some time now. But oh, sorry, Reese's Pieces, I missed your comment. A great mathematician once said, "Good mathematicians understand the analogies. Excellent mathematicians can see the analogies between analogies." That is deep. That is too deep for my 4-beer in mind right now. But no, I get it. Like, the analogies and trying to correlate. All right, so we got to do some predictions. I'm going to pop one up on the screen. We'll see if this one's... There we go. All right, so we're gonna change directions a bit. We have a question up right now. Percent of crude oil that is used for non-energy chemicals. So we drill crude oil out of the earth. A lot of it is put towards things like octane, right? Making gasoline that we can use or diesel fuels. But the question is, what percentage of crude oil is used for non-energy related chemicals? That is things like making plastic bags or polymers or various other things. Fertilizers. Is it less than 20% or greater than 20%? So put your predictions in right now. Is it greater than 20 or less than 20% in terms of all the crap that we pull out of the earth that's hydrocarbon chain? A certain fraction is used for gasoline, fuels, and energy. Sorry, Sachin, the guy in the wheelchair, you got to shoot with a rocket.
Oh, I do.
So tap A.
I was trying to be kind.
To the guy in the wheelchair shooting at you? No. All right, so make your predictions right now. Is the percent of crude oil for non-energy chemicals less than 20% or greater than 20%? If you're not following us, click that follow button right now. You'll get your 300 standard internet units, and you can bet on whether percent of crude oil is towards non-energy related chemicals is less than 20% or greater than 20%.
I have to pick some of this stuff.
So yeah, you gotta. Those are bullets and rockets that you don't need, but you have to shoot a rocket at Mr. Big. Which is the guy
I
in the
thought I
wheelchair.
did. No.
So you have to do them 3 times.
Oh, okay.
Well, that was a good one. This is another RNG fight. All right, so make your predictions now. Percent of crude oil, that is the liquid hydrocarbons that we pull out of the earth in terms of oil drilling. What percent of that we separated into long chains, short chains? What percent of that material is put towards non-energy related chemical production? This includes plastic bags or various other things. This could be, I don't actually know what is produced, but Sachin will tell us when we get the answer to this question. So again, if you're not following, click follow. You can get your 300 standard internet units and you can bet accordingly. What is your bets? And it is closed. All right, Sachin, the percent of crude oil used for non-energy related chemical production.
So that's less than 20%.
Less than 20%.
So approximately 90% is used for energy.
So 90% goes towards gasoline, like methane and crude oil.
Crude oil,
diesel.
either. I mean, a fair bit of it goes to transportation, but there's also like like Tallahassee, for instance. We have natural gas power, right? So that would be like an energy use of right, but so I don't know whether we get it from our natural gas from crude oil, but maybe you do. I don't know the exact source. The remaining 10% makes up, is what we use for basically all our fertilizer. Basically all the polymer we use.
So like every plastic bag at the grocery store falls within that 10%.
Like a lot more than that, right? Because it's like the amount of fertilizer. I mean, maybe you don't use
Tepe rockets. Starting rock. All right, so the answer again was less than 20%.
Yes,
Only
that's
10% of the crude oil that we extract from the earth actually gets applied to things that are non-energy related, so not burnt. I mean, the other 90% goes towards burning it to generate energy. Is that?
Yep, that's right.
That's crazy. I mean, that's a lot of material, like in just terms of sheer volume and mass.
Yep.
That is a crazy amount.
So I looked this up just today. So the daily consumption of crude oil is 100 million barrels, which is, I mean, it sounds like a lot, but it's actually 1 gallon per, like it's between half to 1 gallon per person per day.
Nice.
Finally.
There you go. You got the guy in the wheelchair.
I got him once, or did I get him enough time?
I don't know. Did he crawl away on the ground more
He
than
did.
once?
Okay.
So you got 2. You need 1 more.
Oh, I got 2.
You are very close to the final boss. This is not the final boss.
He's not.
Oh, there you go. That was speed run quality move right there.
Oh, that's not enough. It's like,
Right. A bit astounding. I mean, that's a lot of materials. Oh, there you go. You got it.
oh, I got it.
Oh man, you are almost down to the. You went through this very quick. You committed to the go right and hold gun. Like, it's a good strategy. It turns out it works. All right. Anyone just joining us? Ask a Scientist Gaming expert. Expert science combined with mediocre gameplay. If you have questions for Sachin Shanbhag, please throw them in chat right now. He's an expert in soft materials, modeling things, polymers, DNA, whatever it might be that's not necessarily crystalline in nature or not solids per se, but something slightly between solids and liquids, including non-Newtonian things. He is happy to answer your questions regarding those types of materials. So throw your questions in chat right now, and we will answer them over the next approximately 15 minutes while Sachin plays Mr. Big and tries to beat Mr. Big. So this is a non-trivial fight where you have to actually shoot him in the head.
Oh, in
So
the
you have
head.
to jump and shoot.
Okay.
So you have to get away from him and jump and shoot in the head. And I might have to help him with this. Imagine keeping all your crude oil energy demands for a year in your house with you.
Yeah.
I mean, what would that volume be?
Yeah, it would be about 365 gallons per person per. I mean, if you were an average.
That really, it's a gallon per day?
But that's, like I think a lot of people don't have access to much. I think it's skewed. I think as
It's a
Americans, we use a lot
round
more. Probably
statistic.
10x. I mean, I don't know if it's 10x, but probably more.
Yeah. A gallon per day. I mean, but that's...
But that doesn't, not just transportation, right? That includes.
I mean, that's man, that's so much energy.
I know.
Like, we're not particularly good at using that energy either.
Right.
Like, Carnot cycle gives us what efficiency at burning? It's like,
At most 48, right? Close to 40.
yeah, something like that. In reality, something like 20%.
Probably, yeah.
And so, and that's, yeah. I'm pulling up the average for a lot of folks in Africa.
Yeah,
No,
that
that's
is
true.
exactly right.
Yeah. Oh man, we had that statistic. Who was our guest? I think it was Kennemer actually. It was talking about energy. Was it Justin? Like, who consumes the most energy? And it was a very weird answer for who was the most. It wasn't the United States.
Oh, was it that?
Yeah. It was some.
It was like a Scandinavian company?
No, it was a very particular. I think it was Middle Eastern, very rich company.
Okay,
Or
yeah.
country.
Maybe it's so cheap. It's like water.
Yeah, exactly. All right, throw your questions in chat. If you don't have questions, I am
Got
happy
this.
to answer mine. So one for you. We asked this of a lot of experimental scientists, so I'm not sure what your answer is going to be, but what's the biggest mistake or accident you've seen in lab? This could be financial, this could be experimental.
So I mean, I have a story of somebody who did, who did something like that. Like, he basically burnt a building down. But not at the university. He was a postdoc when I was a grad student.
Okay.
And as a grad student, he was at RPI, and he basically, he burnt a floor, but like the whole building was inoperable for a few days. But that's I feel like I mean, as somebody who does computing, like the most expensive mistakes you make are mostly uh,
Time.
time, right?
Right,
It's the time.
yeah.
I mean, it's a finite commodity, right? And
So you submit a garbage job and
right,
you get an answer, and
it takes a long time. You wait for
Yeah.
it, and it comes back. It's like that answer 42.
Yeah, who cares?
Right? I mean, you don't understand the answer. The answer makes no sense, but you spend a lot of time.
Yep.
And part of you wants to salvage that. But I think the right way to do it is not to have sunk costs and just say, okay, scratch that. But for a brief period of so most of my PhD work was computational, but for my postdoc, I actually wanted to do something different. So I thought I need to do wet lab experiments because I need to be well-rounded, and I just know how to code and write mathematical models, and I should learn how to do experiments. And so I started. And I thought maybe I should do like some biological experiments, like surface and growing cells and stuff like that.
Mm-hmm.
And the problem was I had no skill. Like I had terrible skill.
No.
And
Make no mistake, like anyone that hasn't done experiments, there's a dexterous skill set that you have to develop to actually execute experiments. Like
and
timing and like direction and all that stuff.
and even
matters.
just temperament, right?
Yeah,
I feel like I had debugging can be gut wrenching.
Yeah.
But if something doesn't work in your code, there is a mistake and you can
Yeah.
find it, right? And so, whereas when you're working with cells, you do the exact same thing you did yesterday. But it just turned out that
doesn't work.
the room was
Yeah,
1 degree warmer,
That's
and you
it.
get a completely different,
Yep.
just reproducibility,
Yeah.
and you can't go back and run the exact same experiment.
Yeah, the movie.
And that's very frustrating, right? Because I mean, and then over a period of time, I saw people who had I don't know what it is. Maybe it comes from it's like it's like that. A good experience comes from judgment, and judgment comes from bad experience or whatever, bad decisions and stuff like that. But I saw people who had such an intuitive sense of where things can go wrong, and if something went wrong, where to look, which I completely lacked.
Yeah.
So so I spent about a year doing wet lab experiments, and I don't want to say that it was like a year completely wasted, because I learned that this was not for me, right? I mean, it's a waste if you learn nothing, right? If you're having fun or you learn, that's not a waste. Yeah, but that was expensive in terms of time. Really expensive.
Oh, time
Okay.
and cost and
Yeah, I mean, the cost was my advisor's cost, really. I mean, we actually wrote a few papers out of it, but it took a lot of help from other people. In fact, this was a place where I was the postdoc, but there were grad students who were helping me out. It was completely role reversed.
Texas Space Agency says in AG science, which is presumably agricultural, yeah, you spend a decade running an experiment, and one tractor driver points out a flaw in your experimental design at the first talk you give. I mean, when you have that many variables,
Right.
that's a parameter space. It's brutal.
Yeah.
Faithful Fairy, I heard and have seen many bad stories from my molecular bio colleagues that turned me into an instrumental guy. I mean, it's really like is Mercury in retrograde that affects the outcome.
Yeah.
Like when you have enough parameter space and like one subtle thing, humidity in the room, temperature, like it's pretty brutal.
Yeah.
Speaking of brutal, I'm going to throw up one more prediction right now. So this is our last prediction of the night. If you want to spend your standard internet units, spend them now. If you're not following, click the follow button, get your 300 standard internet units, and bet them on the question that I'm about to post, which is, how much memory does it require to store the entire human genome? And so this is, we're limiting this parameter, right? It was 2 gigabytes per base pair. Is that the right? Or
It's like 2 bits.
2 bits per
So
base
there's
pair.
4 bases, AT, GC, and let's assume you can code them at 0, 0, 0, 1, 1, 0,
Yep.
and 1, 1.
And so if you have 2 bits per base pair, how much storage memory is required to store the entire human genome? Put your predictions in right now. Is it 1 gigabyte or is it 1 terabyte? Make your guess. Sachin, I'm going to take you to the
you
next
probably
level.
should, yeah.
So this is really
Stuck
annoying.
with
I'm
him.
going to show you how to do this. It's You basically need to hit him in the top of the head in a very particular way to get his hat off to do the next
Hat
stage.
off, huh? Whoa.
So it's a jump. You have to shoot him right in the
shoot
hat. There
while
it
you
is. So
jump.
you thought the
Oh.
glasses came off. So now you got to hit him a few times. Now he's a skeleton. So now you can take on the skeleton. And so the skeleton is just bullets, not rockets anymore. I'm sorry. You spent a lot of time wasting.
I'm just stuck to him.
I'm sufficiently drunk that I did not pay attention. All right, storage for the human genome. If you have 2 bits per base pair, how much storage do you need? Is it 1 terabytes or 1 gigabytes? I mean, that's crazy. Like, you remember 10 years ago in terms of USB drives, like how much you could store versus an external hard drive.
I think USB drives are now bigger than like big fat external hard drives.
Yeah, like 1 terabyte doesn't even seem intimidating.
Yeah.
Like it's just a normal data set, which is kind of crazy. And so yeah, this one just run around and shoot its spine until his vertebrae disappear. All right, catching up here. I saw this on the news somewhere. Some kind of fruit that ate them. 5 years of agricultural experiment completely destroyed by some kind of bug that ate the fruit. That is brutal beyond recognition. Detecting moisture in Martian soil. A grad student talked about sensor they used and how did you get that work on Mars. We've spent 5 years trying to get it work in a cotton field. That's a pretty fair critique. All right, so it's done. Human genome, 2 bits per base pair. How much data does it take? Is it 1 gigabyte or 1 terabyte?
You want me to give the answer?
Yep.
So the answer is actually a gigabyte.
1 gigabyte.
It's close to a gigabyte.
That's crazy. That's not even that much storage.
It's not
at
that
this
much
point.
because if it's 2 bits, the average human genome is about 3 billion base pairs. So you can just, that's 6 billion bits. 8 bits is a byte, and then you just do, like you divide. It's not that much. It would fit sort of on an old CD. If you guys remember what that is.
If you guys remember what a CD is, I'm hoping everyone viewing Twitch right now. I think Twitch technically you have to be 18 or older, so I'm assuming they know a CD.
Oh, that's right. If you're 18, right? Okay.
I can't even live stream a barbecue with 1 gigabyte. That's true. There's probably more information in NARC than the human genome, but
but you see, like the other fact about like if you take all the DNA in your body, right? That's a lot of DNA.
Yeah. Yeah, that was a fun factoid, which you tried to do, but Scott Stagg stole it from you. You stretch it out end to end, it's just past Pluto, right?
Right. It goes to Pluto and back, I think, if I'm not mistaken.
Yeah, it's non-trivial. That's crazy.
Yeah.
Like when you think about
right
how long that is.
It's how coiled, like it's stored in a very coiled way. So when it wants to retrieve that information,
not just coiled, but like meticulously structured in a coil. Like it's surgical in how well it packs that DNA in a very small space, which is just it's mind.
And it's sort of even more amazing to me because like the kind of polymers I work with are often called entangled polymers, which is polymers that are sufficiently long, right?
Yeah.
And I mean, you can see, like, I have short hair. My hair don't entangle much, but my daughters have long hair. And it's, like if I don't comb their hair every day, it's a mess, right? So if you have long, strandy objects, they get entangled. Now, DNA is actually much, 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 much longer than most entangled, at the level at which polymers get entangled. The reason they don't get all messed up is because they're like wound on spindles and sort of very carefully stored, and like biology through its random sort of experiments is sort of magical at times, right?
Yeah. Reese's Pieces. I heard you could fit the data for a human DNA on a Nintendo GameCube disc. I mean, that sounds about possible, right. 1 gig is not unreasonable for that. That's 1 gig. That's crazy. That's
not much, right? That's not much at all.
Well,
and
now
in fact,
it's not
apparently
much.
there's like a lot of redundancy. So like if you just want to look at differences between people's DNA. Like a lot of human DNA is conserved, right? So you don't have to store parts that are sort of routinely conserved. So then the number that, so if you really want to store just the places where most of the differences occur, that's just a few megabytes from what I hear. Yeah.
The useful non-epigenetic. Yeah. I mean, that's mind-blowing.
You said I hit the...
Yeah, so run over here and like stand down here. This is not... I've tried to figure out how to beat this boss and I don't have a good answer. But run him way over here. Move up and down just a little bit and then down again. And turn back and shoot at it.
And shoot at its...
Yep, just shoot at it. Sometimes it works, sometimes it doesn't. Go down. It seems like it's completely random. I really don't know how this game works. DNA or texts are easily compressible and are very possible on a disk. Yeah.
Yeah, that's also true. So this is uncompressed, right?
yeah, uncompressed. Yeah, that's a good point. It's worth discussing that parameter space. This game ruined me. I've spent a lifetime doing drugs trying to find one that will turn me into a skull and spine robot. Well, clearly you need to become a drug lord, and then you can become a spine skull robot. That's the dragon you chase for a lifetime. Oh man, I don't know how long it's gonna take. My goal, I'm gonna start speedrunning this game because I've done my homework on it.
Oh,
there it is.
Finally.
The victory. Nice. That deserves GG's. Well done, sir. You finally killed Mr. Big. You've won the war on drugs. Congratulations.
Oh, thank you.
It
was hard.
It was. It's such a messed up mechanism. I'm gonna after you beat this, I'm gonna show you.
Oh, there's one more?
I'm gonna no. You're getting the.
Oh,
the
now
gold.
okay.
So this is the civil forfeiture portion of this, where you steal all the.
And
gold
I take it home
from the drug. Yeah, without trial or conviction. Fun factoid: I actually looked this up because Maine recently they basically abolished civil forfeiture this year. So there are 4 states in the U.S. that have abolished civil forfeiture, and the answer is North Carolina in 1985, Nebraska in 2016, New Mexico in 2015, and Maine in 2021. So any other state that you're in and you get arrested, they can take all money they discover without any trial or prosecution.
Wow.
Yeah, as we've seen in the game NARC. Oh yeah. So if you put an ass, you double your score.
Oh, is that right?
Yep. Nope. So you
isn't that
with the controller?
Like, this is Ask a Scientist, right? That's like the way the British say "aw."
No.
It's like
Ask a Scientist is AAS.
Right, but it's like
ASS. Yeah. So with your controller, ASS. All assets, yes, thank you. All right, victory. We have good game. Congratulations, you won the war on drugs again. There you go. End.
Okay.
Yep.
Oops.
Rub.
Okay.
There we go.
Wow.
Cars, boats, TVs, and tigers. All right, we're almost at the end. I'm going to show you guys a quick run. I have a save state for the final boss here.
Okay.
Here's how you beat the final boss. You have to shoot him in the top of the head, shoot him in the face with a rocket a few times. And then the positioning for how you actually get his vertebrae is completely seemingly random. I don't know the rules that govern it, but you just kind of move positions and shoot.
Well, he's losing them. He just has 4 vertebrae now.
And sometimes like you're in the right position to shoot them and they go away. I don't know the rules that govern this, and apparently nobody that speedruns this does know the rules. It's just like you kind of randomly position until something works. Oh, there you go. You saw 2 of them go away, and then the last 2 are pretty easy. That's it. So this game is absolutely bananas. I don't know how it works. We're going to call it quits there, because that's the end. Sachin, congratulations. You've won the war on drugs. Oh, man. Texas Space Agency, last questions. Do you think it would be possible to model regional variations in barbecue taste based on their social media check-ins? Machine learning.
Machine, yeah. I mean,
Yeah.
you
Yep.
throw the data in, you get something out.
Something, you'd get a
Yeah.
trend of some kind. So,
Yeah.
oh,
Eh,
all right. That's a good question to end on. Sachin, thank you for joining me for Ask a Scientist Gaming. We played through Dynamite Dan, Dynamite Dan 2. We played Super Mario and finally closed by winning the war on drugs with NARC. Thank you all for joining us for Ask a Scientist Gaming. It's been a pleasure. If anyone has suggestions of people that we should raid, please throw them in chat right now. Again, it's been a pleasure. Join us again in 2 weeks. Jim Fadul from a biology department is going to join us talking about neurological pathways and, like, I think it's vision development in zebrafish is what his specialty is. So
Thank you.
again, join us again in a couple weeks for that. Until then, Sachin, any parting words for the audience?
Oh, this was a lot of fun. Thank you, Ken.
So you got to revisit some old games you haven't played in a long time, some new games like NARC.
Oh,
But yeah, it was a pleasure.
yeah, it was a
Again, thank
blast.
you all
Yeah.
for coming by. There were a lot of fun questions, discussion points. We always appreciate when you guys are here. So yeah, again, until next time, it's been a pleasure, and we'll see you then. Stick around. We're gonna raid some kind of science education expert. We'll figure out who that is in the next minute or so. So again, until next time, we'll see you guys at the next Ask a Scientist Gaming in 2 weeks.